Good day, everyone. How are you doing today? All right. I am Ede David Chibuzo, the current president of National Fellowship of Christian Pharmacy Students, and we are, as at the time of recording this video, and we are going to be teaching you or guiding you on a video tutorial on chemical and ionic equilibra under PCH 231. And the material which we are going to be used is the material that was released by the immediate past HOD as at the time of recording this video of the pharmaceutical chemistry department, Professor M.O. Agbo. So we're going to be looking at some very basic things in chemical and ionic equilibra, and we do believe that if you follow this tutorial from the start to the end, you're able to grasp everything in the material. And towards the end of this video, we'll look at some of the sample questions that is released at the back of the material. Just in case you don't have the material, you can check the description below and download the material for free. All right, so let's talk about chemical and ionic equilibra. When we talk about chemical and ionic equilibra, we're talking about it in view of the fact that as pharmacists, you're going to be dealing with drugs, and drugs are usually weak acids or weak bases. So in view of that, it's very important to understand how it relates to pharmaceutical chemistry and be able to understand a few things about this drug, even as you progress in your professional career. So we happen to have drugs that are weakly acidic or weakly basic. And here we have list of acidic drugs and we have list of basic drugs. Now, under the classification for acidic drugs, we have drugs that has carboxylic acid functional group. Carboxylic acid functional group is the COOH group. So an example is aspirin, and that's the structure we have here. This is aspirin. This is the structure of aspirin. So it has a carboxylic functional group. This is the carboxylic functional group. And that's what gives is that acidic nature that is present. This is an ether group, so this an ester group, it does not give it any of the acidic property. This is what gives it its acidic property. Another example is methotrexate for treatment of cancer. This is furosemide, is an agent that is used as a diuretic, a high saline loop diuretic. So we have drugs with phenolic group. That's another class of acidic drugs we have in pharmacy. And an example is paracetamol. So the structure of paracetamol is drawn as follows. Yeah. I think I need to get something clear. All right, so this is the structure of paracetamol, and this is a benzene ring. So this is the structure of paracetamol. It has a phenolic group here, and this gives it the acidic nature that is possessed. And why is it called paracetamol? Because in the placement of functional groups in pharmaceutical chemistry, in relation to the particular functional group you are dealing with, the position next to it is referred to as auto position. The position 2 steps away from it is referred to as meta position, and then 3 steps away from it is referred as para position. So the reason why this is called paracetamol is because the phenolic group is para to the amine group that's present here. So this is an example of an acidic drug, and this structure I said is the structure for paracetamol, because the phenolic group is para to this NH group here. Then we also have levotyrosine, which is also related to the amino acid, and it's an example of an acidic drug. Then under the basic drugs, we have drugs that have the amino functional group. This is the amino functional group here. And then we have phenylbutazone. This is the structure of phenylbutazone. This is the structure of phenylbutazone. This is the structure of phenylbutazone. So you can find the amino groups present here, and they are responsible for the basicity of that particular drug. Then we also have indomethacin. Indomethacin happens to be a pain reliever, and it's a basic drug. Then we have another drug, basic drug, that is also having a phenolic group. We have the morphine. Morphine is also an opioid analgesic, so it helps to relieve pains. It helps to relieve pain. So these are examples of acidic drugs and basic drugs. And as you progress as pharmacy students, you're definitely going to be getting more insight into these different classes of drugs. So we'll progress quickly to discuss about the theories of acid and base. We have the Arrhenius theory, we have the Brusted and Lowry concept, then we have the Lewis concept. So we'll start with the Arrhenius theory. According to Arrhenius, describes acids as substances that hydrolyze in water to release protons, to release hydrogen ions as protons, while Arrhenius also describes bases as substances that dissolve in water to release hydroxide ions. Take note of that. For Arrhenius, according to his theory, acids are compounds that dissolve in water or hydrolyze in water to release protons or hydrogen. When we say protons, we are referring to hydrogen in this concept. And then bases are substances that hydrolyzes in water to release OH, that's hydroxide ion. What that simply means is that according to Ionic, even compounds that do not have OH in the first place, if they can dissolve in water or hydrolyze in water to release OH, according to Ionic, such substances are referred to as base. A very good example of that which I just described now is amines. So we have amines. Amines dissolve in water plus H2O. Amines dissolve in water. So give us this. All right. So amines dissolve in water to give us this. What this goes to show us is that this compound, according to Ionic, can be referred to as a base because it hydrolyzes in water to release hydroxide ions. Same thing you talk about when you talk about the acidic aspect of it. Any substance that dissolves in acid to release protons or hydrogen is referred to as an acid in terms of Ionic theory. But this particular theory has a limitation. And what is the limitation? The limitation is that it is dependent on the presence of water. It is dependent on the presence of water. So water is the limitation for this. For you to define acid and base under Ionic theory, you need water. So that's the limitation it has. It means that in the absence of water, you can't really be able to define an acid or a base in terms of Ionic theory. Another theory we're going to be looking at is the Bronsted and Lowry concept. For the Bronsted and Lowry concept, an acid happens to be a proton donor. That's a substance that donates proton. And I said proton in this context refers to hydrogen ion. So acid are referred to as proton donors, while bases are referred to as proton acceptors. So if a compound donates proton, according to Bronsted and Lowry concept, it is referred to as an acid, and if a substance accepts proton, it's referred to as a base. A very good example of this happens to be HCl. Let's look at HCl. In the presence of water. Meanwhile, it's very important for you to take note of the fact that in Bronsted and Lowry concept, anything that dissolves in water is not even seen as something that dissolves in water. It's seen as something that reacts with water. And that's what I want to show you using HCl and water. Normally, when you put HCl in water, you say the HCl has been dissolved in water. But in Bronsted and Lowry concept, in terms of the proton acceptor, proton donor relationship, it is said that HCl is reacting with water. Because when HCl reacts with water, it is going to produce oxonium ion. It's going to produce oxonium ion plus Cl minus ion, that's chloride ion. Now this can be called oxonium ion, this can be called hydrozonium ion, and this can also represent hydrogen ion. So it is just water being captured in there for that particular purpose. So you can call it oxonium ion or you can call it hydrozonium ion. So HCl reacting with H2O gives us hydrozonium ion or oxonium ion with chloride ion. What's happening here? The HCl donated proton to the water. So in this case, water accepted the proton and is referred to as a base, while HCl donated the proton and is referred to as an acid. And like I said, acids in terms of Bronsted and Lowry are proton donors, while bases are referred to as proton acceptors. Bases are referred to as proton acceptors. So let us do another example and then we make progress. Let's look at the example of NH3. Let's look at the example of NH3. So let's look at the example of NH3. Now when you work with NH3 plus H2O, in this case, hydrogen, H2O donates proton to the NH3. You now have this. You now have this. So the NH3 accepts proton from the water and it now forms ammonium ion and then hydroxide ion. Now because this NH3 collects or receives proton, accepts proton from the water, it's referred to as a base because according to Bronsted and Lowry, bases are proton acceptors. And because the water is what donates the proton, in Bronsted and Lowry concept, the water is referred to as an acid. So this is a very, very simple stuff you have to learn. Now, what limitations do Brusted and Lowry concepts bring on board? The limitation it brings on board is that it is dependent on the presence of hydrogen. The limitation it brings on board is that it is dependent on the presence of hydrogen ion, or you call it proton. On the presence of hydrogen ion or proton. What it means that if there's no hydrogen ion, there's no proton, it means you cannot be able to define anything in terms of Brusted and Lowry concepts. All right, now there's something very interesting I will need to bring to your notice here. This definition is also captured when it comes to the reactions of paracetamol. So if when paracetamol donates this hydrogen here, it is seen as an acid because it is a proton donor, according to Brusted and Lowry concept. Just a side thing for you to know. Meanwhile, the major focus I want to focus here is the concept of conjugate acid and conjugate base. The concept of conjugate acid and conjugate base. Now, whenever you have a protonation of a species, when I say protonation of a species, I'm simply talking about addition of proton to any species. That species that is formed after protonation is referred to as a conjugate acid. That species that is formed after protonation is called a conjugate acid. While when you deprotonate a species, that is, you remove proton from a species or remove hydrogen ion from a species, whatever is formed is referred to as a conjugate base. So let us look at an example of this. Now look at let's look at NH3 plus H2O. Now NH3 accepted hydrogen. That means ammonia was protonated with hydrogen. So what is formed there is ammonium ion, and this ammonium ion is referred to as the conjugate acid of ammonia because hydrogen ion slash proton was added to ammonia. Meanwhile, if you look at the reverse reaction where you have ammonia being converted back to ammonium ion being converted to ammonia, you see that there's a loss of proton or the protonation of the species. Now, by reason of losing proton to form ammonia, in this case, in the opposite case, ammonium remains the acid and then ammonia is now called the conjugate base. All right, so for the purpose of clarity, I will have to clean this asset of the board. Let us take it much more slowly so I can capture it with key examples that will help you to assimilate the concept being discussed about conjugate acid and conjugate base. Conjugate acid and conjugate base. So let us do it this way. Let us do it this way. So a species plus proton slash hydrogen ion will give us the conjugate acid. Are we together? All right. Then a species minus proton slash hydrogen ion will give us a conjugate base. So we call this addition of proton, we call it protonation, and we call the removal of proton, we call it deprotonation. So this is as simple as it can be. So let us have practical examples. So this is NH3 plus H plus. What is it going to give to us? It will give us NH4 plus because you now have 4 hydrogen, and then this is NH4 plus. This compound now is going to be called the conjugate acid of NH3. The conjugate acid of NH3. Meanwhile, this is the reverse. The reverse is going to be NH4 plus losing hydrogen to now form NH3 plus H plus. Now, this reverse case shows us that NH4 now in this case is going to be acting as the acid, while NH3 that lost proton is going to be called the conjugate base. Now, whenever you have these pairs together, NH3 slash NH4 plus, this is referred to as a conjugate acid slash base pair. So this is a conjugate acid base pair. Are we together now? Conjugate acid base pair. So I've done an example using ammonia and ammonium. So let us use another compound to drive our points home. So let us look at H2CO3. This happens to be triazocarbonate 4 acid. Now H2CO3, when it loses hydrogen or ion, is going to be HClO3 minus plus H plus. Now, this one lost proton, so when it loses proton, what it forms is the conjugate base. So this is the acid and this is the conjugate base. If you do the reverse, it is going to be called, this one will now be called the base, and then this will be called the conjugate acid. This is another example. What other example can we use here? Again, let's try another example. This is H2SO4. This is tetrahydrosulfate 6 acid. H2SO4 can lose hydrogen and we are able to form HSO4 minus plus H plus. This is the acid and this is the conjugate base. This is the acid and this is the conjugate base. There are many more examples of conjugate acid base pair that you interact with, but one underlying principle is that whenever there's a protonation of a species, what is formed is the conjugate acid, and when there's a deprotonation, what is formed is the conjugate base. It cannot get simpler than that. So that's a simple definition of that. Now, there's something you have to note here. For example, we have a compound like HCl. HCl can lose hydrogen ion to form H plus plus Cl minus. Yeah, you are correct to say that Cl minus is the conjugate base of HCl. But take note, Cl minus on its own cannot act as a base. Cl minus on its own cannot act as a base. Here is why. There's a general principle in chemistry that the anions of strong acids as well as the cations of strong bases are neutral in solution. So I'll write the word here, neutral. Or they have neutral pH. Let's put it that way. Anions of strong acid and the cations of strong bases are neutral in solution. So they don't have basic properties in solutions, even if they can be referred to as conjugate bases of the respective acids from where they were derived. An example of anion of strong acid happens to be our Cl. Example is the Cl minus. Another example is NO3 minus. These are anions of strong acid. In solutions, they do not cause a change in pH. They are neutral in solution. They don't cause a change in pH. Meanwhile, cations of strong bases, we have examples of strong bases. We have things like sodium hydroxide. So the cation is Na plus for sodium hydroxide. We also have potassium hydroxide, that is K plus. That's K plus. We also have calcium hydroxide, that's calcium plus. I don't know. No, calcium may not really be a strong base, but then we have sodium, we have potassium, we also have others like the aluminum and the likes. But what you need to go home with is the fact that anions of strong acid and cations of strong bases do not cause a change in pH. This Cl, just in case you are wondering where it's coming from, this is from HCl. HCl is a strong acid, hence it is coming from there. NO3 is coming from HNO3. This is triazonitrate 5 acid. It's a strong acid. For the bases, we have NaOH, we have KOH. That's where I got the cation from. So these are the cations for strong bases, and then these are the anions. These are the anions for strong acids. So you can capture that there. So these anions and cations of strong acids and strong bases, respectively, do not cause a change in pH. Why this is going to be important is because subsequently we'll discuss about it. And if you're not able to capture it at this point, you may want to stop the video and go back and digest it appropriately. So let's go to the last theory of acid and base, which we'll be discussing in this particular tutorial, which is the Lewis concept. Now, according to the Lewis concept, acids are electron acceptors. Now you see the language have changed. It has moved from proton to electrons. So according to Lewis, acids are electron. I'll write electron at the top, please. Acid are electron acceptors, while bases are electron donors. So for Lewis, what is considered in Lewis happens to be electron. What is considered in Lewis happens to be electron. So according to Lewis concept, we have that acids are electron acceptors and then bases are electron donors. So we have a reaction here between ammonia and boron trifluoride. We have a reaction here between ammonia and boron trifluoride. Now you can realize here that ammonia happens to have a nitrogen that has a lone pair of electrons. Now, according to the KLMN shells that are discussed in chemistry, we know that what we have here in the orbitals for N happens to be 2, 5 because nitrogen is actually having an atomic number of 7, so it has 7 electrons, and by implication we have 2 in the innermost shell and we have 5 at the outermost shell. Now out of these 5, we already have 1, 2, 3 bonding with hydrogen. So what is left? 5 minus 3, that's going to give you 2. So what is left is 2. These 2 electrons, this nitrogen or this compound as a whole is going to donate it to boron trifluoride. And boron trifluoride is going to accept it because it actually has some space in its orbital. It's going to accept these 2 electrons that are captured here. Now, according to Lewis says that acids are acceptors of electron. Which of them is accepting electron? The boron trifluoride. According to Lewis, bases are donors of electron. Which of them is donating? The ammonia. So according to Lewis, this happens to be the base and this happens to be the acid. And then you're going to form a coordinate bond. You're going to form a coordinate covalent bond. Now, if you go back to your normal basic chemistry, we have different kind of bonds. We have the normal ordinary covalent bond, and we have the coordinate or dative covalent bond, and that's what's going to be formed in the case of Lewis concept. So you have electron acceptors being defined as acids, and you have electron donors being defined as bases. Now, Lewis acids are known as aprotic acid. What does aprotic acid simply mean? Aprotic acid simply means that it's not capable, that particular acid is not capable of donating proton. It's not capable of donating proton. There's no dissociable hydrogen in that particular acid, so it's aprotic. Now, compounds that there are compounds that react with bases by accepting pairs of electrons, not by donating protons. Do you see that now? So aprotic simply means that they cannot donate protons. Instead, they just accept pairs of electrons. Examples of Lewis acids: we have the boron, we have the boron trifluoride, and we have the boron trichloride. All right, so back to it. We have seen the limitation of Arrhenius theory. We have seen the limitation of Breasted and Lowry concept. What about the limitation of Lewis acid? Can you guess that? All right, so the limitation of Lewis acid is as follows. The limitation is that there must be lone pair of electron. There must be lone pair of electron because we are defining acid and base in terms of electron acceptors and electron donors. So there are no lone pair of electrons. You cannot be able to apply the Lewis concept. So I'm going to be making progress on this tutorial from this point on. Thank you. All right, so we're going to be discussing about dissociation constants. We're going to be discussing about dissociation constants. I'm going to make progress to discuss about the dissociation of monobasic acids and monoacidic bases in water, and then discuss how we can calculate the pH in terms of chemical and ionic equilibra. Now, dissociation constants from basic chemistry, you already know that it's represented by the symbol or the letter K. So dissociation constant simply refers to the constitution of the product over the constitution of the reactants. The ratio you have there refers to the dissociation constant. So what we have here is the dissociation equation for an acid, a sample acid, Ha plus H2O dissociating into H3O plus A plus. The reason why we have a two-way arrow is because dissociation is not complete. That is typical of weak acids and weak bases. They usually will not have complete dissociation, so there's always like a back and forth motion until there's equilibrium from both sides. Now, why exactly are we adding H2O to this particular equation? Because normally we can actually say HA dissociates into H plus then plus A minus. This is A minus, sorry. H plus A minus. You can say HA dissociates into H plus A minus. Why are we adding H2O? The reason we're adding H2O is because pharmaceutically, the solvent that is more commonly used in pharmaceutical operation happens to be water. So you have to factor in water into your dissociation so it can be more realistic. And secondly, when we talked about the Brusted and Lowry concept, as well as the concept of the Arrhenius theory, find out that water happens to play a major role in those two concepts. So we're going to be cleaning this right away, and then I'm going to be explaining something very key that will help us to make progress here. So I'm going to be showing you how we can calculate the dissociation constant for acids. For base, this is a base plus H2O. We know that base is actually a proton acceptors. So this guy B accepted proton, and then base is when it dissolves in water, they release hydroxide. So it's releasing hydroxide. Those are the theories we just discussed some moments ago. Then this is water. Water undergoes autoprotolysis or ionization to give H plus, that's proton ions, and then OH minus. Now, this happens to be autoprotolysis of water, or the ionic ionization of water. Now, I want to show you something. Let's calculate the dissociation constant of water, and then I will explain something that is very key. Dissociation constant for water is K. We will have a subscript W to represent that this is the dissociation constant for water. So it's going to be, I told you that the dissociation constant happens to be the multiplication of the concentration of the products over the multiplication of the concentration of the reactants. So the product we have here happens to be H plus. In chemistry, whenever you see square bracket simply indicates concentration. So we have H plus times, I don't need to add the times, it's optional if you want to do that, but once you have brackets side by side each other, it simply means that it's multiplication. So that's H plus multiplied by OH minus, that's hydrogen ion, divided by what are the reactant. What's the reactant? The reactant here happens to be H2O. The reactant here happens to be H2O, so you put the concentration of H2O. So this is how to calculate the dissociation constant for water. So but there's something I want to bring to your notice. It is about this water here. Now, the concentration, the molecular concentration of water is very high. And because it's very high, when it involves in all of these kind of reactions, the changes that are there are so insignificant that it is considered that the water there, the concentration remains constant. And as such, they don't usually feature it in calculation of dissociation constant. So usually they remove the water molecule because of the fact that it is the molecular concentration of water is too high and it's almost considered constant, and hence it is not featured when you are calculating dissociation constant. So this particular reaction or this equation can now reduce to H plus multiplied by OH minus, because you are removing this water by reason of that reason which I just gave right away. So this is dissociation constant of water can now be calculated directly by using H plus concentration times OH minus concentration, excluding the presence of water, because water is, the molecular concentration is so high that it's almost considered constant when you have to do with calculation of dissociation constant. Hence, it's not necessary in this equation. So with that in mind, we can now write out the dissociation constants of the acid, dissociation constant of the base, and then we can make progress. So let us try for that of the acid. That of the acid will be Ka equal to what are the products we have there? We have ozonium or hydrozonium ion multiplied by A minus ion divided by H A ion. Are we going to add water? No, we are not going to add water because I already gave a reason why water is no longer necessary. By implication, we'll leave the water aspect blank. So the only thing that will be considered there will be HA. So this is the dissociation constant for the acid. And then for the base, let me write this by this side because of the space factor. So for the base, the product for the base happens to be BH plus multiplied by OH minus divided by, we're not going to add water because I've already explained that to you. What we're going to be adding is just the base. So this is the concentration of the base. So that is the dissociation constant of water, dissociation constant of acid, and then the dissociation constant of base. Now this Kw is referred to as the autoprotolysis constant of water, or you can also call it ionic product of water. Autoprotolysis constant of water, or the ionic product of water. And it's important that I bring to your knowledge that for this particular Kw usually it varies with temperature and some other factors, but usually the value is around 1 times 10 raised to the power of minus 14 at 25 degrees Celsius with a unit of mole square dm minus 6. Yeah, that's very understandable because you know that concentration is in mole per dm cube. So when you have 2 moles multiplying, that's mole square, and dm cube per dm cube, that's dm minus 3 multiplying. So you have dm minus 6. So we have 1 times 10 raised to the power of minus 14 mole square dm minus 6 around the temperature of 25 degrees, but it can vary around this range. But this is like an approximate value for kW of water. Now, we have what is called pKW. We have what is called pKW. So pKW happens to be like the negative logarithm of the dissociation constant of water. If you do a negative logarithm of this, what I'm simply saying is if you do minus log of 10 raised to the power of minus 14, what you're going to get is 14. So the pKW of water, that's the negative logarithm of the dissociation constant of water, is going to give you 14. What does that bring to mind? It simply means that the multiplication of the concentration of the hydrogen ion and then the hydroxide ion is also going to give you 14. So let us do something here. So we have pKW equal to, we are aware that when we begin to introduce logarithms to this, you no longer use multiplication. Instead, it is converted to plus sign. So pKW is equal to pH. What is pH? pH is equal to the negative logarithm of hydrogen ion concentration plus pOH. What is pOH? pOH is the negative logarithm of the hydroxide ion. So we know that this pKW is 14. So we know that pH plus pOH is going to give us 14. From here, what is pH? I already explained that. That is already a basic chemistry term. pH is negative logarithm of the hydrogen ion concentration. It's going to give you, so base 10, very, very important. It's going to give you the pH. So pH plus pOH is going to give you 14, which is like same value as the autophotolysis constant of water, negative logarithm of the autophotolysis constant of water. So I think these are just basic things you need to look at. Meanwhile, Ka is the dissociation constant for acid and the dissociation constant of base. What you can still be able to calculate for pKa. You can also be able to calculate for pKb. The reason why we can calculate for that of water is because experimentally it has been determined that Kw is somewhere around 1 times 10 raised to the power of minus 14. But for different acids and base, they will have different pKas and different pKb. So you don't have any fixed values for them. But for that of water, you have fixed values for them. So let us look at some weak acid and weak base, and let's begin to consider their pKa and also consider their calculation of their pH. Now we have the dissociation of weak monobasic acids and bases. Now we have monobasic acids. When we say monobasic acids, we're simply talking about acids that have one ionizable or replaceable hydrogen ion. An example of monobasic acid happens to be HCl, because when you dissociate HCl will dissociate to give us H plus plus Cl minus. So this is one replaceable hydrogen ion. That's why it's called monobasic. The basicity is 1. Another example is HNO3. HNO3 is monobasic because it has H plus plus triazonitrate 5. All right, are we together now? So that is monobasic because it has just 1. But we also have other types of acids. We have dibasic acids, we have tribasic acids, and the like. So an example of dibasic acid, very popular, happens to be our sulfuric acid. Sulfuric acid, which according to IUPAC, International Union for Pure and Applied Chemistry, IUPAC called it tetraoxosulfasis acid. So this is H2SO4. H2SO4 will dissociate into 2 hydrogen ion plus SO4 2-. So this is having 2 replaceable hydrogen ion, hence it is referred to as a dibasic acid. So but in this context, what we'll be looking at are monobasic acid. Then for bases, we have monoacidic bases, we have diacidic bases. When we talk about monoacidic bases or diacidic bases, we're talking about bases. For monoacidic bases, we're talking about bases that release just 1 hydroxide ion, while diacidic bases are bases that release 2 hydroxide ions. An example of monoacidic base happens to be NaOH. When NaOH dissociates, NaOH is going to give us Na plus plus OH minus. This is 1 hydroxide ion. So NaOH is monoacidic. It's an example of a monoacidic base. Meanwhile, for dibasic base, we have bases like MgOH2. So MgOH2, when it dissociates, is going to give us Mg 2 plus OH minus 2OH. Now this 2OH makes this NGOH2 a diacidic base. These are just basic normal chemistry fundamentals. I'm just trying to bring here so you understand the idea of monobasic acid and monoacidic bases. So we're going to be looking at case 1. We have case 1, which is a case of a weak acid in water. When a weak acid dissociates in water, for you to calculate the pH, there are two formulas we have. Now take notes. In that material, there happen to be a derivation of this particular formula. You can learn that for your own good. But for the purpose of examination writing, you may not necessarily need to know how to derive the formula, except your lecturer specifically asks you to master that. But it's not necessary. What is necessary is, do you know the formula to calculate for a case of a weak acid dissociating in water? The pH is equal to half pKa minus half log C. What is C? C refers to the concentration of that particular solution. So you can also put them in brackets and say bring out the common factor, which is half brackets pKa minus log C. Another way you can move to calculate it is using the quadratic equation. And in the quadratic equation, what you are going to calculate for is the concentration of the hydrogen ion, which is equal to negative Ka plus square root of Ka square minus 4KAC over 2A. When you are calculated for the concentration of hydrogen, you will now use this formula for you to calculate for the final pH. So depending on the context of the question and which of them you are more comfortable with, you do your calculation. Simple tip. If you can master this, you can bring back anything that is given to you back to this. But if you want to go the long way, it is still your own choice. It's fun to always try different methods. But for the purpose of time, we are going to be working with the first, which is the simplest method for calculation. So we'll look at 2 examples here in the case of weak acid in water, and we'll make progress in this tutorial. So the first question says, for the given sample of 0.01 mole per dm cube of benzoic acid, what does this tell us? This is a case of a weak acid in water. How do we know it's a weak acid? Because we know that organic acids or organic acids are weak acid, and this is benzoic acid. Benzoic acid is represented by the formula C6H5COOH. This is benzoic acid. Are we together now? So you have benzene and then removal of one hydrogen, addition of a carboxylic acid group. We don't need to draw that, but let's you can have a pictorial sample of it. So this is a benzoic acid. This is benzoic acid. It's a weak acid, and then it said calculate its pH given that Ka is equal to 6.5 times 10 raised to the power of minus 5. So when benzoic acid dissociates, we are going to have C6H5COO minus this benzoic ion, and then you have H plus. So that's the dissociation of benzoic acid. Meanwhile, our focus here is going to be to calculate the pH. What do we need in calculating the pH? We need the pKa and we need the log C. What is the C? C is the concentration. Take notes. Whenever you are solving things like this, make sure that your concentration is in mole per dm cube. If it is not in mole per dm cube, you convert it to mole per dm cube. Some examples we'll be looking at here. For example, this particular example is going to show you the step-by-step procedure for converting any unit you have back to mole per dm cube. So pay very close attention and you'll master it and become a pro as you do the practice of these things. So we have the C, but what we don't have is the pKa, but we have Ka. What did I tell you that P? Whenever you see anything like P, this P is in small letter, it simply tells you negative logarithm to base 10. So pKa is negative logarithm to the base 10 of Ka, while pKb is negative logarithm to the base 10 of Kb. So we have Ka there. So let us solve for the negative logarithm to the base 10 of Ka. So our pKa is equal to negative logarithm of our Ka. What's our Ka? 6.5 times 10 to the power of minus 5. So you get a scientific calculator and then you do the calculation. Negative logarithm of 6.5 times 10 to the power of minus 5 is equal to 4.187. So this is our pKa. Can we calculate for our pH now? Yes, we can do that. Our pH is equal to 1 over 2. pKa is 4.187 minus log C. Let us do the log C straight away, and then we'll put that into what we have in the bracket. So log C is minus 2. Log C is minus 2. So in mathematics, minus times minus is going to give us plus. So what we have here is pH is equal to 1 over 2, 4.187 plus 2. And that's going to be 1 over 2 times 6.187. So our pH at the end of the day is going to be 3.0935. And so one decimal place, if you like, you can make it 3.10. So this is the pH of the sample of benzoic acid that was provided, calculated using that simple formula. So that's the formula you just need to master and you can make progress. Meanwhile, you can use this other formula to do your calculation. You have your Ka, you have your C. But whenever you are done calculating for the hydrogen ion concentration, you must come back and calculate for the pH using this formula. This is actually more easier. But if you want to test that the other way, you can actually do that. So calculate the pH of a 50 milligram per ml solution of ascorbic acid. Do you see that? Another organic acid there. Ascorbic acid is a weak acid, and we're talking about weak acid in water. So this formula still applies to it. So in your exams, nobody's going to tell you whether it's a weak acid or a weak base. You just have to see it and know whether it's a weak acid or a weak base. As you do more examples, you get more familiar with how the questions can come in. So molecular weight is 176.1 and the pKa is equal to 4.17. We have our pKa, and what we need is our concentration. And I told you before that concentration has to be in mole per dm cube, but what we have here is milligram per ml. So how do we convert from milligram per ml to mole per dm cube? There are just a few things you have to note. So let me wipe the board quickly so that you can follow me very clearly on this part of conversion from any unit you have down to mole per dm cube. When you're able to get it right this first time, you'll be able to follow me through in the remaining part of this tutorial video that is covering everything about chemical and ionic equilibra. So we have, all right, so what we have here is that, take note of this, very, very important. 1000 cm cube is equal to 1000 ml and is equal to 1 dm cube, which is same thing as 1 liter. Are we together? So 1000 cm cube is something as 1000 ml and it's equivalent to 1 dm cube, which is something as 1 liter. If you have this thing in your head, you can go to convert your volumes down to dm cube. You can go to convert your volumes down to dm cube. Another formula that is very important for you to note is that concentration in mole per dm cube is equal to concentration in gram per dm cube over the molar mass. The molar mass, which is given in gram per mole. So the concentration in mole per dm cube is equal to concentration in gram per dm cube divided by molar mass, which is always present in gram per mole. So when you have this relationship, you can go to get the concentration in mole per dm cube. And you already know that for you to convert 1000 milligram is equivalent to 1 gram. You already understand that very, very basically. So let us convert for ascorbic acid and then we do our calculation. All right. So let us do the conversion. Let's do it in our solution, the solution space we have here. So we have that 50 milligram is present in 1 ml. We have that 50 milligram is present in 1 ml. So the first thing we'll convert from our milligram to gram, and then we'll convert from our ml to dm cube. 50 milligram is in 1 ml. 50 milligram is present in 1 ml. I'm trying to look at the way I'm going to solve it so that you don't get confused. 50 milligram is present in 1 ml. Okay, let us convert the milligram to gram. To convert to gram, do 50 divided by 1000. So we're going to have 0.05 gram is present in 1 ml. All right, that is perfect, very perfect. So for here we can make progress. So I converted milligram to gram. 50 milligram is something as 0.05 gram, because for you to convert from milligram to gram, you simply divide by 1000, because if 1000 milligram is equal to 1 gram, 50 milligram will be equal to 50 times 1 divided by 1000. So that's 0.05 gram. So if 0.05 gram is present in 1 ml, X gram will be present in 1000 ml. X gram will be present in 1000 ml. So what you simply do is that you do multiplication of the opposite sides and divide both sides. Now what that simply means that X will multiply 1, 0.05 will multiply 1000, and then you divide both sides by 1, because that's what you're going to have there. X gram times 1, let's just do it for the purpose of this first example so you can get it clearly. Subsequent examples, I may not waste so much time here. So let us just get it at the start, so as you follow through with the video, you understand very clearly. X gram times 1 ml is equal to 0.05 gram times 1000 ml. So what you have here is X gram times 1 ml equal to 0.05 gram times 1000 ml. So what you now simply do is to divide both sides by 1 ml, so you can make X the subject of formula. You divide both sides by 1 ml, so you can make X the subject of formula. So when you do the division, you are going to have that X gram is equal to 50. So what we have is 50 gram. 50 gram present in where? 50 gram present in 1000 ml. And I've told you already that 1000 ml is something as what? 1 dm cube. So it means that 50 gram present in 1000 ml is something as 50 gram per dm cube. Makes sense, right? Yeah, so that is 50 gram per dm cube. But we are not done. The question says that we should calculate for the pH, and we are told that concentration must always be in mole per dm cube, but this is gram per dm cube. This is one step towards our final solution. We will now implement our next formula, which says that concentration in mole per dm cube is equal to concentration in gram per dm cube divided by molar mass. Just in case you get confused while listening to this part of the video, you can rewind and listen to it again very clearly, because it is as clear as possible. So the concentration in gram per dm cube, we have gotten it. What about the molar mass? The question gave us the molar mass as 176.1. So can we get our concentration in mole per dm cube? Yes, we can get it. So our concentration in mole per dm cube is now equal to 50 gram per dm cube divided by our molar mass of 176.1 gram per mole. So what's our concentration in mole per dm cube? What's our concentration in mole per dm cube? So we have 50 divided by 176.1. That's going to give us 0.2839 mole per dm cube. 0.2839 mole per dm cube. So that's our concentration. Now that we have concentration and we have pKa, we can simply solve for our pH. Our pH, anytime you are going to write this course as a theory, make sure your P is in small letters. I don't know if you're getting it, but if it's an objective exam, you don't necessarily need to pay attention to that. pH is equal to 1/2 pKa minus log C. So we don't have so much space there, so I'll do the minus log C on my calculator. What's our C here? Our C is 0.2839. So we have 0.56 or 46. So it's going to be 1/2 brackets. What's our pKa? According to the question, pKa is 4.17. 4.17 minus 0.5468. So our pH is equal to, I don't need to put the 1/2, please. You just solve along with me. We are having limited space here. 0.5468 divided by 2. So our pH is going to end up being 1.8116, which is approximately 1.81. So the pH of this particular solution is 1.81. So the next example we're going to be looking at is going to be about the case of a weak base in water. So let's make progress. All right, so we just noticed an error in this calculation. So if you follow very clearly, it says 1/2 pKa minus log C. What is our pKa? Our pKa is 4.17. What's about log C? Our log C is log of 0.2839. Log of 0.2839. That's going to give us this. Now remember, pKa minus, that is 4.17 minus, so let us open bracket to give our log C. Our log C, according to our calculation, is minus 0.5468. Minus 0.5468. So when we do that calculation, we are going to be doing our correction right away. I'm going to do our correction right away. So when you are going to do that, minus times minus is going to give you plus. Minus times minus is going to give you plus. So all you have is 4.17 plus 0.5468. And then you divide by 2. Our answer is going to be 2.3584, which is approximately 2.36. So our pH, the correct pH value for this solution is 2.36. So let us make progress and talk about the case of weak base in water. All right, so we are going to be considering a second case, a case of a weak base in water. A case of a weak base in water. So what we have here is we have two formulas that you can use to work on weak bases in water. We have pH equal to pKw minus 1 over 2 pKb plus 1 over 2 log C. That's one equation you can use for weak base in water. Another equation you can use is pH equal to 1 over 2 pKw plus 1 over 2 pKa plus 1 over 2 log C. What's the difference between these two equations? We have pKb here, we have pKa here, and then we have half pKw plus, we have just pKw minus. So any of them you want to stick with, I will advise you that you just take one and master it. Any question that comes in that line, you can use that particular one to solve it. But if you're a genius, you may want to consider having two of them in your head, but be sure that in the examination hall, you will not end up misplacing them. Any of them you use will give you the same answer. It has been tested and proven. When we solve with one of them, you can do the other one, and then you see that the answers will eventually be the same. So the first question says calculate the pH and pOH. Take note, there are two things you are calculating for, pH and pOH, for a 0.001 mole per dmq solution of ammonia. A solution of ammonia is going to be ammonium hydroxide, and that is a weak base. So it means that what I'm talking about here is a weak base in water. Remember what I told you in your examination, nobody will tell you that it's a weak base in water, nobody will tell you it's a weak acid in water. You just have to see the question and know which of the formulas you have to apply. So this is a solution of ammonia, which is ammonium hydroxide, and it's a weak base in water, given that Kb at 25 degrees Celsius is 1.75 times 10 raised to the power of minus 5. So let us look at the parameters that have been given to us. We have the concentration, and then we have the Kb. So the things we can look at now, we know what is pKw. From the start of this video, I already told you that pKw is the negative logarithm of the autophotolysis constant of water, which is 14. pKw is 14. And then our pKb, we are given pKb, we are given Kb, we can find pKb. And then if we want to solve for pKa, we can still be able to solve for pKa, because pKa plus pKb will still end up giving you 14. So any of them we choose to work with, we give you the same answer. So for the purpose of this video, I'm going to work with the first formula, and then we're going to solve right away. So let us go. So the first thing we'll solve for pKb, so we can apply the formula. Our pKb is equal to negative logarithm of Kb. And what's our Kb? Minus log our Kb, according to the question, is 1.75 times 10 raised to the power of minus 5. So if you punch that into a scientific calculator that is well calibrated, we'll have minus log 1.75 times 10 raised to the power of minus 5, and that's going to give us 4.756, 9. So at the end of the day, you can approximate it to 4.76. So this is our pKb for ammonia solution, that's ammonium hydroxide. We have our pKb, and I've told you already that pKw is equal to 14. So the next thing for us to apply is for us to apply our formula. Meanwhile, we can actually still calculate our log C here for saving of space. Our log C is equal to logarithm of 0.01 mole per dmq. We are aware that this is already in mole per dmq, so no conversion is going to be necessary. So we have log 0.001 mole per dmq. That's going to, our log C is going to be minus 3. So let us feed that into our equation. The first one, we are going to have pH equal to pKw. What's pKw? 14 minus 1 over 2. What's our pKb? Our pKb is 4.76 plus 1 over 2. What's our log C? Our log C is minus 3. So we're going to have pH equal to 14 4.76 divided by 2 is 2.38. Plus times minus will give us minus. So this is minus 2.38 plus minus 3 divided by 2 is going to give us minus 1.5. Minus times plus. Okay, let us just take that a little bit slow. 1.5. So that's going to be pH equal to 14 minus 2.38 plus times minus will give us minus 1.5. So our pH is now going to be equal to 14 minus 2.38 minus 1.5, and that's going to give us 10.12. So the pH of the solution of ammonia, which is 0.001 mole per dm³ with a Kb at 25 degrees Celsius of 1.75 times 10 to the power of 5, is going to be 10.12. If you end here, you will be losing marks because the question says calculate the pH and the pOH. So let's calculate for the pOH. We are aware that pH plus pOH is equal to 14. What is pOH? pOH is equal to 14 minus pH, and that's going to be 14 minus 10.12. So 14 minus 10.12 is going to give us 3.88. So we have found the two things that they asked of us. So our pH is 10.12 and our pOH is 3.88. With that, this question have been deciphered. In case when you are watching this video, you encounter any difficulty and you have any question to ask, you can ask in the comment section of this particular video, and answers will be given to you promptly by the academic team of the National Fellowship of Christian Pharmacy Students, UNN chapter. So number 2 question says, calculate the pH of 1% weight by volume solution of ethanolamine. Ethanolamine, we already told you that from the beginning of this video that basic drugs, they have a amino functional group. This is an amine functional group featuring here. This is a weak base in water. So most amine drugs are usually weakly based or weak bases. Now when they find expression in weak base in water, you can use any of this formula for you to solve that. So this is ethanolamine, and then they are given the pKa of 9.4. So can we solve for this? We are still going to use the first formula. Like I told you, any of them works. You choose which one you want to work with, and you can go to go ahead with it. So let us use the first formula here. So we know that pKw is 14. So we don't need to solve for that. Our pKb, we are given pKa. How do we get pKb? I already told you that pKa plus pKb is going to give you 14. So when you know the pKa, you can go to know the pKb by just simply doing 14 minus 9.4. Then what about the log C? Our C is supposed to be in mole per dm³, but what we have here is 1% weight by volume. So you need to convert 1% weight by volume into mole per dm³. So let us know how to solve that. From your pharmaceutical calculations in 200 level, you would have learned that 1% weight by volume simply means 1 gram is present in 100 ml. This is weight and this is volume. 1% tells you in 100. So this is 1 gram present in 100 ml. There are many other scales for this. You have many other scales for this, but you find more expressions for these things in your pharmaceutical calculations. You can visit Ansell's textbook for that, either edition 13 or 15, or whatever edition existing as at the time when you are watching this video. 1 gram present in 100 ml. But we know that we don't need gram in ml. What we need is mole per dm³. So let us solve and first of all get gram per dm³. So 1 gram is present in 100 ml. S gram will now be present in 1000 ml. Why 1000 ml? Because we know that 1000 ml is something as 1 dm³. So if 1 gram is present in 100 ml, S gram will be in 1000 ml. Do you remember the formula? You simply do cross multiply this times this divided by 100. So our S gram being subject to formula is equal to, if you get confused there, just revert to the previous examples where I did this. So this is S gram equal to 1 times 1000, 1 times 1000 divided by 100. That's going to give us 10 gram in 1000 ml. So if 1 gram is present in 100 ml, it means that 10 gram is present in 1000 ml. If 10 gram is present in 1000 ml, we know that 1000 ml is 1 dm cube, it simply means that the concentration of this solution is 10 gram per dm cube. But we are in gram per dm cube, and we are supposed to get it to mole per dm cube. Do you remember our formula for mole per dm cube? Concentration in mole per dm cube is equal to concentration in gram per dm cube divided by the molar mass in gram per mole. Now we have gram per dm cube. The only thing we don't have here is the molar mass of ethanolamine. They are gracious enough to give us the formula for ethanolamine. Meanwhile, I did not write the dissociation formula for ammonia. I did not write for ethanolamine. We can leave that aside if you don't need that. But you cannot actually see the formula, the equations in your material. I would have written that out, but it will not be necessary anymore since we have gone past that point in the tutorial. So, but you can actually see that in your material. Since we're in ethanolamine, let me just write the formula for that. That's going to be H2NCH2OH plus H2O to yield, since it's a base is going to accept proton. And why will you accept proton? Because this nitrogen here has lone pair of electrons. So we're going to have, it will yield H3N plus CH2OH plus OH minus. So this is what it's going to yield because of the presence of the lone pair of electrons on the nitrogen. It's going to accept the proton that is being added to it. So according to Lewis' concept, this is the electron donor, while according to the Bronsted and Lowry concept, this is actually the proton acceptor, which is the base. All right, so this is the equation. Is for your own consumption. Meanwhile, our focus here is on calculation of the molar mass. So the molar mass can be calculated as follows. Molar mass of ethanolamine. We can calculate it this way. So how many hydrogen do we have here? We have, hydrogen has a molar mass of 1. So we have, for this 2 hydrogen, that's 2. 2 plus 2 plus 2 plus 1. So that is 2, 4, 6, 7. So for the hydrogen, we have 7. You can decide to do it slowly and just be doing 2 plus nitrogen. Nitrogen is 14. So you can do 2 plus 14 plus 12 plus 2. Okay, let's do it that way. I think it's going to make it more simpler for you. So for hydrogen, we have 2 plus nitrogen is 14. That's the atomic relative atomic mass, RAM. For carbon, carbon is 12. For hydrogen, it is 2. It's 1 for 1 hydrogen, but because it's 2 hydrogen, we have 2. For carbon, it's also 12. And then for hydrogen, 1 for 1 hydrogen, but for 2 hydrogen, it will be 2. In normal calculations, you put that in bracket as 2 times 1, which will still give you 2. And then for oxygen, oxygen is 16. And then for hydrogen, it is 1. So can we add that together? That's going to be 2 plus 14 plus 12 plus 2 plus 12 plus 2 plus 16 plus 1. And that's going to give us 61 gram per mole. So the molar mass of ethanolamine is 61 gram per mole. So can we calculate now for the concentration in mole per dm cube? Yes, we can calculate in the concentration in mole per dm cube. So permit me to clean this so I can have sufficient space for solving of this problem. So we have concentration in mole per dm cube equal to, what's the concentration in gram per dm cube? 10 gram per dm cube. So that is 10 gram per dm cube. And what is the molar mass? Our molar mass is 61. So this is 61 gram per mole. So the concentration in mole per dm cube is going to be given as 10 divided by 61. And that's going to give us 0.1639 mole per dm cube. Per dm cube. So that's 0.1639 mole per dm cube. So the next thing for us to now do is for us to calculate. You can use this, you can use this. All right. Now, let's say we are going to use the first one. So let us work with the first one. Our PKB, I told you that PKA plus PKB is equal to 14. So our, then we have to manage the space we have here. Our PKA plus PKB is equal to 14. Hence, PKB will now be equal to 14 minus pKa. And what's our pKa? 9.4. So 14 minus our pKa is 14 minus 9.4, and that's going to give us 4.6. So our pKb is 4.6. So let us calculate for our pH right away. Our pH is now equal to pKw. What's pKw? 14 minus 1 over 2 pKb, which is 4.6, plus 1 over 2 log 0.1639 mole per dm cube. So let us bring that down. That will now be pH equal to 14 minus 4.6 divided by 2 minus 2.3. Then we have log 0.1639. That's going to give us minus 0.7854. Minus times plus. Okay, you have to divide by 2. Then minus times plus is going to give you minus. So you now have minus 0.3927. So what we now have as our pH final value will now be 14 minus 2.3 minus 0.3927. And our final answer will be 11.3. So this is the pH, 11.31. So this is our pH of the ethanolamine solution. So the next question we're going to be solving is to calculate the pH of a saturated solution of codeine monohydrate. Now the codeine here, this INE here, tells you that they happen to be like somewhat of an amine functional group in that particular compound. Codeine monohydrate. Monohydrate just tells you that it is having one molecule of water attached to it. Because of that amine, that nitrogen present in it, it happens to be a weak base in water. Hence, it fits into our weak base in water calculation. So the pH of a saturated solution of codeine monohydrate having a molecular weight of 317.4, given that its pKa is 8.2 and its solubility at room temperature is 1 gram in 120 ml of water. So let us calculate the pH. What do we need for this calculation? We will still stick to equation 1. Whenever you are solving, you can use any of the equations, you will get the same answer. So we'll still stick to equation 1. The question already gave us what we need to calculate, which is the pH. We know our pKw is 14. Our pKb, we are given pKa. We are given pKa as 8.2. So all we have to calculate for is the pKb. And we now have to get pKb, right? We know our pKb is equal to 14 minus pKa, which is 14 minus 8.2. 14 minus 8.2. 14 minus 8.2 is going to give us 5.8. So our pKb is 5.8. Meanwhile, if I'm working with this one directly, we will not need to do any conversion, but it will still give you the same answer. You can do your findings and tell me what you think about that in the comment section. So let us make progress. The next thing we need is the C, which is our concentration in mole per dm cube. But what we have here is gram in ml. And it says it is 1 gram present in 120 ml. Can we do our conversion? Yes, we can. X gram will now be present in 1000 ml. Our X will now be equal to 1 times 1000 divided by 120. So that will be 1000 divided by 120, and that's going to give us 8.33 gram in 1000 ml. And since that is 1 dm cube, that will be 8.33 gram per dm cube. One step already been made, but we must get our concentration in mole per dm cube. So our concentration in mole per dm cube, we have been given the molar mass as 317.4. So our concentration in mole per dm cube is going to be equal to 8.33 divided by 317.4. In case you are wondering where it's coming from, this is where it's coming from. So this is 8.33. 8.33 divided by 317.4, and that's going to give us 0.0262 mole per dm cube. So the concentration of codeine monohydrate saturated at room temperature is 0.0262 mole per dm cube. Can we calculate for our pH now? Yes, we can. Our pH is equal to, what's our pKW? Our pKW is 14. 14 minus 1 over 2. Our pKb, according to our calculation, is 5.8. 5.8 plus 1 over 2 logarithm of our C log 0.0262. So our pH is equal to 14. 5.8 divided by 2, that's going to be minus 2.9. Then logarithm of 0.0262. So that's plus, you divide by 2, so that's going to be plus minus 0.7908. So our pH is now going to be equal to 14 minus 2.9. Plus times minus is going to give us minus, and around 0.7908. So that's going to be 14 minus 2.9 minus 0.7908. 08, and that's going to give us our pH. Our pH is going to be 10.3092. Our pH is approximately 10.31. So this is the pH of codeine monohydrate saturated solution. Is that easy? So the next thing I'll just briefly discuss before we go into hydrolysis of salt will be the dissociation of polyprotic acid and bases. When we talk about polyprotic acids and bases, we're talking about acids. In the case of acids that can donate more than one hydrogen ion or more than one proton ion. I already gave an example of diabasic acid like sulfuric acid, and we have other acids like the citric acid, we have the tartaric acid, and we have other examples of such acids. Meanwhile, for bases, we're talking about bases that can accept more than one hydrogen ions into their compound. Meanwhile, as it relates to drugs, we have different drugs that are polyprotic, and we have different drugs that are polyprotic acids and polyprotic bases. You can see examples of such in your materials. One thing you have to note about them is that the dissociation of such drugs or such compounds follow a gradual process. Dissociation of such compounds follow a gradual process. So for example, let's use H2SO4 as an example. Let's say H2SO4 wants to dissociate. H2SO4 wants to dissociate. The first dissociation of H2SO4, meanwhile, this is a poor example to use, is going to be HSO4 minus plus H3O plus. This is a first dissociation. Second dissociation will now be HSO4 minus plus H2O will now give us SO4 minus plus H3O plus. So what you need to note about this is that the dissociation constants for the different level of dissociations are different. That's basically what you need to know, and then every other detail you need is available in your material. So the next thing we'll go to quickly is the hydrolysis of salts in water. And when we talk about hydrolysis of salts in water, hydrolysis simply means hydrolysis. Lysis means breakage. It means cutting, dividing apart. Hydro simply means that water is involved. So when we talk about hydrolysis, we're talking about dissociation of compounds in the presence of water. And we're going to be talking about that in relation to salts. In your basic chemistry, you already know about acidic salts, basic salts, normal salts, double salts, and the like. So you see how it influences chemical and ionic equilibria. All right. So what we're going to be focusing on, like I mentioned, is hydrolysis of salts. Hydrolysis of salts. So hydrolysis, I simply tell you that that's actually dissociation of compounds in the presence of water. All right. So we're going to be looking at the different cases of hydrolysis. We have salts that form from strong acid and strong base. We have salts from strong acid and weak base. We have from strong base and weak acid. We also have from weak acid and weak bases. These different salts, when they dissociate in water, they produce solutions that have different pH. So you're going to be seeing how you can calculate the pH of those different solutions and know how you can be able to put them in calculations and calculate appropriately. So we'll start with the salts of strong acid and strong base. An example of such salt happens to be sodium chloride. Sodium chloride is formed from strong acid and strong base because it's formed from the combination of NaOH plus HCl to give NaCl plus H2O. This is a strong base, sodium hydroxide. This is a strong acid, hydrochloric acid. So it gave us sodium chloride. So that's the sort of a strong acid and a strong base. So if sodium chloride is going to dissociate in water, if sodium chloride is going to dissociate in water, sodium chloride will dissociate into Na plus Cl minus. If you decide that you want to add water to this equation, the water molecule itself will also dissociate. If you decide to add water to this equation, let's say you start to add H2O here, the water molecule will also divide into H plus OH minus. Now, you have equal amount of hydrogen ion and equal amount of hydroxide ion. The pH is 7. What about the Na plus Cl minus? Do you remember when we talked about conjugate acid and conjugate base? Yes. The anions of strong acid and the cations of strong base are neutral in solution. They do not cause any change in pH. What it means is that the sodium chloride here, the sodium here do not cause any change in pH. The chloride here do not cause any change in pH. And then you have equal amount of hydrogen ion and hydroxide ion. It simply means that the salts of strong acid and base, when they undergo hydrolysis, the pH will be equal to 7. So if you are given a salt that is formed from strong acid and strong base, and you are asked to tell what is the pH, and you look at it, there's nothing written, no concentration, no pKa, and you are confused. You don't need to be confused, because the pH for strong acid and strong base undergoing hydrolysis will be 7. The explanation is that the anions of strong acid and the cations of strong bases do not cause any change in pH. They are neutral in solution, and hence when those salts dissociate or undergo hydrolysis, they do not cause any change in the pH. So the next case we have is a case of strong acid and weak base. Strong acid and weak base. That means the salt we are talking about here happens to come from a strong acid and come from a weak base. An example of such salt is going to be, let's try this salt. Let's look at NH4 2SO4. NH4 This is ammonium tetraoxosulfate 6 salt. Ammonium tetraoxosulfate 6 salt. Let us go back and see where it's actually formed from. It's formed from H2SO4 plus NH4OH. It gave us NH4 2SO4 plus H2O. So let us balance that out. This is going to be 2 here, and this is going to be 2 here. So let's check whether that's complete. We have 2 hydrogen plus this. That's going to be like 2. Okay, the NH4, we have NH4 2 out already. So we have 2 hydrogen, 4. So that's 4 hydrogen. We have SO4, we have SO4. We have 2 oxygen, we have 2 oxygen. So this is a balanced equation. So this salt, ammonium tetraoxosulfate 4, is coming from H2SO4, that is tetraoxosulfate 6 acid, according to IUPAC, old name sulfuric acid, and ammonium hydroxide. This is a strong acid, and this is a weak base. Strong acid, weak base salt undergoing hydrolysis, automatically the pH is going to be less than 7. Remember that less than 7 gives you acidic, and then greater than 7 gives you basic. So it's going to be less than 7, hence the pH is going to be less than 7, because you're having a strong acid that is more acidic than the weak base. So let us look at the dissociation that is going to give us an idea of how this whole process takes place. NH4 2SO4 is going to dissociate into 2 NH4 plus SO4 minus, 2 minus. Do you remember what we said about anions of strong acid? Anions of strong acid do not cause any change to the pH. So this guy do not cause anything at all to the pH. What we have here is 2 NH4 plus. Now 2 NH4 plus in the presence of water, is going to dissociate and donate proton to water to form H3O plus. Let's leave this 2 out. H3O plus our NH3. So it's going to dissociate and donate proton to water to give H3O plus NH3. When you have H3O plus increasing and then the OH is not increasing proportionally, automatically the pH is going to go down, because you have more of hydrogen ion than the hydroxide ion. So this is dissociation that leads to the decrease in pH, because more hydrogen ion will be in the solution as opposed to the hydroxide ion that is supposed to balance it out. So a sort of strong acid and weak base will lead to a solution that has a pH that is less than 7. And the formula for calculating it is similar to the formula for calculating a case of weak acid in water, which is pH equal to 1/2 pKa minus log C. So if you know the formula for calculating weak acid in water, that same formula we're going to apply here. So let us apply it in this particular example. We have calculated the pH of 0.05 mole per dm cube of ammonium chloride. pKb is equal to 9.25. Ammonium chloride was what was given to us here. So can we look at ammonium chloride? This is ammonium chloride. This ammonium chloride, and I can easily deduce that ammonium chloride came from a combination of hydrochloric acid plus NH4OH to give NH4Cl plus H2O. So this is a strong acid and this is a weak base. Automatically, I can apply this particular formula. So, but let us look at the dissociation first of all. Dissociation will give us NH4 plus Cl minus. This is an anion of a strong acid. I already mentioned that for anions of strong acid, they do not cause any change in pH, so they are neutral in solution. What we have here left is NH4. Our NH4 plus water, if you choose to add water, will dissociate into H3O plus NH3, no sign there. So this is increase in the hydrogen ion concentration. An increase in the hydrogen ion concentration will lead to a decrease in the pH. So you have a pH value that is less than 7. Just in case you don't want to add water, you can simply do NH4 plus dissociating into H plus NH3. This is also valid, but I've told you the reason why we add water, because water is like the most common solvent used in pharmaceutical industry. Nevertheless, let us make progress. So our question says we should calculate the pH. That's what is interesting in this question. So we have 0.05 mole per dm cube. Our constitution is already in mole per dm cube, and we had pKb. Can we get pKa? Yes, we can get pKa, because we know that pKa is equal to 14 minus pKb, because we know that pKa plus pKb will give us 14. So we have 14 minus our pKb of 9.25. 14 minus 9.25, that's going to give us 4.75. So our pKa is 4.75. Our pKa is 4.75. So let's calculate for the pH. Our pH is now equal to 1/2 pKa, that's 4.75, minus, in brackets, log C. What's our C? 0.05 mole per dm cube. So we have our pH is equal to 1/2 brackets 4.75 minus log 0.05 is going to give us minus 1.3010. So we're going to do minus times minus will give us plus. So what we're going to have is pH is equal to 1/2 brackets 4.75 plus 1.3010. So we're going to have our pH equal to 4.75 plus 1.3010 divided by 2 is going to give us a pH of 3.0255, which is approximately 3.03. So the pH of this solution is going to be 3.03. The pH of that solution is going to be 3.03, and 3 is less than 7. So that is the calculation for that. So we're going to be looking at a second example, and we're going to be making progress in that regard. We're going to be looking at a second example, and we're going to be making progress in that regard. Okay, I think there's somewhat of a problem we have here. The problem we have here is that this is supposed to be the pKa, This is supposed to be the pKa for that particular solution. So it's supposed to be the pKa for that particular solution for us to have this. Alright, this is supposed to be the pKa for that particular solution. Sorry for that misconception. So I'm going to be going over it again very quickly. It's supposed to be the pKa for that solution. I made a mistake while writing the question. It's supposed to be the pKa for that particular solution. I made a mistake while writing the question. So let us correct that quickly. let us correct that quickly. So where the pKa is 9.25, we don't need to look for pKa again. So simply put 9.25, 9.25, 9.25, and our final pH will be 9.25 plus 13010 divided by 2, and that's going to be 5.2755, which is approximately 5.28. So the pH is 5.28. Sorry for that writing error. It's pKa, not pKb. So let's look at the second example that says, calculate the pH of 5% weight per volume of oxycodone HCl with pKa of 8.9 and molecular weight of 405.9. Now we have our pKa, but what we need is our concentration. Our concentration here is given is 5% weight per volume. Another question is, how do you know whether it is a salt of a strong acid and a weak base? This is oxycodone and this is HCl. HCl happens to be a strong acid. Oxycodone is a steroidal molecule that is weakly basic. So by implication, we have a sort of strong acid and weak base. HCl can also be called a counter ion. It's an ion that counters what's already originally present in the compound. Since this is basic, you need a counter ion that is acidic. And then when you have an acidic compound, you need a counter ion that is basic. So let's look at let's look at how to convert that weight per volume to mole per dm cube. I already told you earlier on that 5% weight per volume simply means gram in 100 mil. So 5% weight per volume simply means that 5 gram is present in 100 mil. So S gram will be present in 1000 mil. Our S is now equal to 5 times 1000 divided by 100. 5 times 1000 divided by 100, and that's going to give us 50 gram in 100 mil, but then 1000 mil, and then I told you that 1000 mil is something as 1 dm cube, so that's going to be 50 gram per dm cube. That's going to be 50 gram per dm cube. Then the next thing for us to do is to convert from gram per dm cube to mole per dm cube. So we know that the concentration in mole per dm cube is equal to 50 divided by what is the molar mass? The molar mass will be given to us as 405.9. So when you calculate that, 50 divided by 405.9, that's going to give us 0.1232 mole per dm cube. So can I calculate for our pH? Our pH is equal to 1 over 2 bracket pKa. Our pKa, according to the question, is 8.9. 102 bracket 8.9 minus our log C. What's our C? 0.1232. So we can now calculate for pH. Our pH is equal to 1 over 2 bracket 8.9. What is log C? Log 0.1231 is going to give us minus 0.9097. Minus times minus will give us plus. So we have plus 0.9097. So our pH, our final pH will be 8.9 plus 0.9097 divided by 2, and that's going to give us 4.90485, which is approximately 4.90. So the pH of the 5% weight per volume of oxycodone HCl is going to be 4.90. So the next case we have is a case of sort of strong base and weak acid. Now in the case of strong base and weak acid, you find out that the base is going to cause the pH to go higher because it's counterbalance the weak acid that is supposed to bring the pH down. So the pH for strong base and weak acid will be greater than 7. Will be greater than 7 because we have a strong base and then we have a weak acid. Can we get a source to exemplify this? Yes, we can have a source to exemplify this. The salt we're going to be using, the salt. We're going to be using Na2CO3. We're going to be using Na2CO3. Now, Na2CO3 happens to be a salt that comes from NaOH plus H2CO3. So NaOH plus H2CO3 is going to give us Na2CO3 plus H2O. This is a complete equation. It actually goes in phases. The first phase or the first batch of it is supposed to be, this is 2 now. If I'm not mistaken. So I have 2, 2, 2, yes, and this is 2. Alright, so the first phase was supposed to be NaOH plus H2O. It will form NaHCO3, and then finally now forms the Na2CO3. There's no space for us to do that phasing. But the idea is that it's coming from a strong base and a weak acid to form Na2CO3. From a strong base and a weak acid to form Na2CO3. When you work on this, the dissociation, when you work on the dissociation, you have Na2CO3 in addition to water. In addition to water, it's going to give us 2Na plus HCO3 minus. Okay, let's check that out. Let's check that out. We are going to be getting to. Okay, that's going to be quite complex. That's going to be quite complex. I have to let me remove the water so I don't have to cause a problem for my own self. So let me remove the water so I don't have to cause a problem. But then maybe later I can resolve that. Na2 plus CO3, just doing the direct conversion, you have Na plus CO3 minus. Now, this is Na plus. Na plus is a cation. Na plus is a cation of a strong base. So this is not going to be influencing the pH. NH plus is a cation for a strong base. It is not going to be influencing the pH for that particular solution. NH plus is a cation for Na plus is a cation for a strong base, so it's not going to be affecting the pH of that particular solution. It's not going to be affecting the pH for that particular solution. So I think I've gotten what I was supposed to write in that first one. That's actually very important, so I can show you the dissociation completely. This is going to be H2O. H2O is going to lead to Na plus, that's 2Na plus HCO3 minus plus OH minus. Yeah, that's what I was supposed to write. So we have Na2CO3 plus H2O to give 2Na plus. I think that this is not going to cause anything in the solution. We have HCO3 and then hydroxide. Hydroxide is already increasing the pH. Nevertheless, the HCO3 minus is still going to work with water. HCO3 is still going to work with the water. Still going to work with the water. To dissociate into CO3 2 minus plus CO3 2 minus. I'm coming please so that I can be able to write the correct things there. It's still going to work with the water. So it's still going to work with the water to give H2CO3 plus OH minus. Yeah, that's what I'm supposed to write. So it's still going to work with the water to give H2CO3 plus OH minus. It has already released hydroxide ion, and it is releasing more hydroxide ion. By implication, the pH is going to be going up. So it's going to be greater than 7. All of this explanation is just for you to get the idea that strong base and weak acid upon hydrolysis will give you a pH that is greater than 7. So, but then this will only be very important for you to understand if you are going to write in a theory exam. If it's not a theory exam, you may not necessarily need to understand this. What we need to understand is how to apply the formula into this calculation. For your notice, you will have realized that the pH is equal to 1/2 pKw plus pKa plus log C, all brackets. This formula sits right with the last formula we used when we are dealing with the cases of weak acid in water. So let us come down and then do our calculation of this. We'll do another example and then we'll make progress to the final case, which is the case of weak acid and weak bases. So let us solve this. Let's calculate the pH of 0.05 mole per dm³ solution of sodium acetate. Sodium acetate goes by the formula CH3COONA. CH3COONA is the formula for sodium acetate. Acetate happens to be the old name for ethanoate. So this is sodium ethanoate according to the International Union for Pure and Applied Chemistry, IUPAC for short. Now CH3COONA is coming from two things. We have CH3COOH, that's ethanoic acid, reacting with NaOH. Ethanoic acid is a weak acid. NaOH is a strong base. So when you have CH3COO reacting, it's going to dissociate into CH3COO minus plus Na plus. Remember what we said about the cations of strong base, they do not cause any change in pH. So we have CH3COO minus plus H2O is going to yield CH3COOH plus OH minus. So more OH ions will be released into the solution, thereby causing the pH to be greater than 7. So let us solve for this. Now we have our concentration, and we have our pKa, and we have our formula. Can we get our pH? Yes, we can get our pH. Our pH is equal to 1 over 2 bracket. pKw is 14 plus our pKa is 4.66, and then our log C is log 0.05 mole per dm cube. So our pH is equal to 1 over 2, 14 plus 4.66. Log 0.05 is minus 1.3010. Minus times plus will give us minus 1.3010. So our pH, our final pH, will be 14 plus 4.66 plus minus 1.3010 divided by 2, and then our pH finally is 8.6795, which is approximately 8.68. Can you see that 8.68 happens to be greater than 7? It shows that what we have here is a sort of strong base and a weak acid. We'll do one more example, and then we'll go to the last case, and then from there we can now make progress to talk about amphiprotic salts and the likes. All right, so we are going to be continuing with the second example under the case 3, which is the case of a strong base and a weak acid. And like I've told you already, the formula which we use for that is the formula we also use for case of weak acid and weak base in water. So the question says, calculate the pH of 600 milligram of benzyl penicillin sodium. What does sodium tell you? Sodium is a counter ion, and the sodium tells you that it is a cation that is coming from a strong acid. So it could be sodium hydroxide or any other sodium, whatever, but it is coming from a strong base. So by reason of this strong base, that's already a strong base. What about the benzyl penicillin? Benzyl penicillin happens to be a weak acid. So what we have is a combination of a strong base and a weak acid. And I've told you before that this is a counter ion for benzyl penicillin. So just like the oxycodone hydrochloride, I told you that the hydrochloric acid is strong acid, oxycodone is weak base, HCl was a counter ion there. Here you have a weak acid and then a strong base. So the sodium there is a counter ion for the benzyl penicillin. So it applies to this particular case in 2 ml of water for injection. We already know the formula for this, and we are going to be looking for two things. We are going to be ensuring our concentration is in mole per dm cube, and we are going to be calculating for the pH. So let us calculate for the concentration first of all. Our concentration here, they said that 600 milligram is present in 2 ml of water for injection. This is not your concern. Your concern is 600 milligram in 2 ml for the purpose of this calculation. So we have 600 milligram present in 2 ml. Can we convert the milligram to gram? Yes, we can. To convert from milligram to gram, you simply divide by 1000. 600 milligram divided by 1000 will give you 0.6 gram present in 2 ml. If 0.6 gram is present in 2 ml, S gram will be present in 1000 ml. That will be S equal to 0.6 times 1000 divided by 2. So we have 0.6 times 1000 divided by 2, and that's going to be 300 gram per dm cube. That's going to be 300 gram per dm cube. So we already have the concentration in gram per dm cube. The next thing for us to do now is for us to convert this to mole per dm cube. And we already know that concentration in mole per dm cube is equal to concentration in gram per dmq divided by molar mass, and the molar mass given to us is 356.4. So we have 300 divided by 356.4 is going to give us 0.8418 mole per dmq. So this is 0.8418 mole per dmq for the benzene penicillin sodium. The next thing for us now to do is to calculate our pH. Our pH is equal to 1 over 2 pKw plus pKa 2.76 plus log C, which is log 0.8418 close bracket. So our pH is equal to 1 over 2 14 plus 2.76 plus log 0.8418 is going to give us minus 0.0748, and then we're going to have our pH is equal to 1 over 2 bracket 14 plus 2.76 plus times minus will give us minus 0.0748. So our final pH value is now equal to 14 plus 2.76 minus 0.0748 divided by 2, and our value is going to be 8.3426, which is approximately 8.34. So the pH of the solution is 8.34, and you can already see that 8.34 is greater than 7 because this is formed from the salt of strong base and weak acid. Alright, so the next case we have here is case 4, a case of salt of weak acid and weak base. Because we have weak acid and weak bases, weak acid and weak base will not undergo complete dissociation in water. So what the pH is supposed to be is to be a pH of 7. It's supposed to be a pH of 7, which is neutral. But the challenge we have is that the degree of dissociation of the weak acid and the weak base is dependent on several factors. So unlike for strong acid and strong base, we know that there's a complete dissociation, irrespective of whatever strong acid or strong base, you will have a complete dissociation to have a neutral pH. But for weak acid and weak bases, the dissociations for the different acid and the different bases are different. So they have different dissociation constants. Hence, even if it's supposed to be a neutral pH, depending on the weak acid and the weak base that form the salt, you may not have a neutral pH. For example, we have a salt of a weak acid and a weak base, which happens to be CH3COO-NH3. This happens to be ammonium ethanoate. Ammonium ethanoate is formed from ethanoic acid and NH4OH, which is our ammonium hydroxide. So this particular salt is formed from two weak, this is weak acid and this is weak base. So when it dissociates in water, let us do the dissociation equation. Let's do the dissociation equation so that you can follow through very clearly. Alright, so this is supposed to be, this is 4, please. So when we do the dissociation equation, we're going to have this 4, we're going to dissociate, and it's going to dissociate into CH3COO minus plus NH4 plus. So let us do the dissociation for each of these particular products. So for CH3COO minus plus H2O will give us CH3COOH plus OH minus. So this is going to lead to increase in pH. What about for NH4 plus? For NH4 plus H2O, for NH4 plus H2O, we'll have H3O plus NH3. This is going to cause a decrease in pH. So if the amount of H3O plus ion released balances the amount of OH minus ion release, the pH is supposed to remain neutral at 7. But I told you that the dissociation constant for the weak acid and the weak base responsible is going to affect the pH. So even if it's supposed to be a pH of 7 neutral, it may not be neutral depending on the weak acid and the weak base, their dissociation constant. So let us see that featuring here. So this is the formula for calculating. Okay, let me infer what I'm saying now. Let's imagine that the dissociation constant for the acid and base is actually equal. Let's say pKa is 5 and pKb is 5. 5 minus 5 will give us 0. This is pKw 14. 14 divided by 2 will give you 7. So the pH automatically would have been 7. But when you have a different dissociation constant for the acid and a different dissociation constant for the base, automatically the pH cannot be 7, even if it's supposed to be 7. So let us calculate for this. The question says 100 milligram per mil of chlorphenamine malate. Chlorphenamine, amine, tells you that this is a weak base, and then malate comes from malic acid, which is an organic acid, which is a weak acid. So it fits into the condition of sort of weak acid and weak base. So our chlorphenamine malate, molecular weight of 390.8 in water for injection, and the pKb is chlorphenamine 5.0, pKa for malic acid is 1.9. You can already see that they have different dissociation constants. So by implication, the pH for this solution is not going to be exactly at 7. So let us calculate, let's see whether we can get something from here. So we have pH is equal to 1 over 2. Remember that when you are writing pH, the P is supposed to be small. 1 over 2 pKw. What's pKw? That is 14. Plus, what's our pKa? Our pKa is 1.9. What's our pKb? Minus, what's our pKb? Our pKb is 5.0. Do you realize we're not using concentration here? So even if they are providing molecular weight, whatever they are providing is none of your business. What's your business is what's the formula, and then you work with the formula. So we have our pH is now equal to 1 over 2. So we have 14 plus 1.9 minus 5.0 divided by, okay, that's going to be in bracket 10.9. So we have our pH is now equal to, so when you divide that by 2, it's going to give you 5.45. So do you see that now? We have our pH being less than 7 because of the differences in the dissociation constant for the weak acid and the weak base. So that's the case of weak acid and weak base. So the next case we have here is for amphiprotic salts. We are talking about monobasic acid and base. We are talking about polyprotic acid and base. Now we are talking about amphiprotic salts. Amphiprotic salts are salts that have both basic and acidic properties. That means they can react with acid and they can react with base. An example of such salt happens to be the hydrogen triazocarbonate 4 ion, and then we have the hydrogen triazosulfate 6. So we have those two salts, they actually have amphiprotic characteristics. And when they dissolve in water, they give amphoteric compounds. For example, what we have here, we have HCO3 minus reacting with hydrogen ion. That means this is going to be acting as a base, reacting with an acid to form H2CO3. Meanwhile, in this place, when it's just dissociating, it's going to be acting as an acid donating proton. We said that an acid is a proton donor. So here it is donating proton acting as an acid, while here it is accepting proton acting as a base. So it has both acidic and basic properties. So it's an amphiprotic salt. So for you to calculate the pH of amphiprotic salt, you simply do pH equal to 1 over 2 pKa1 plus pKa2. What is pKa1? pKa1 is the ionization constant for the acid, while pKa2 is the ionization constant of the base reaction. So for this reaction now, the dissociation for this guy will be pKa1. Dissociation constant for this one will be pKa2. When you add it together, do divide by 2, you get the pH for that. So the next thing we're going to be going over is going to be the buffer solutions. So you can learn about buffer solutions, and from there we can progress towards the end of this tutorial. Alright, so what we're going to be talking about now, we're going to be talking about buffer solutions still under PCH 231. So chemical and ionic equilibra. So for buffer solutions, what are buffer solutions? Buffer solutions simply refers to solutions that resist changes in pH on addition of small amounts of acid or base. So when you have solutions that resist changes in pH on the addition of small amounts or base, such solutions are called buffer solutions. And what makes them to have that buffer capacity is due to the reserved acidity and reserved basicity we have in such solutions. So usually there are two types of buffer solutions. We have acidic buffers and we have basic buffers. So for example, an acidic buffer, buffers are usually done with their conjugates. So an acidic buffer is usually made up of a weak acid and its conjugate base. You know how we form conjugate base? By the removal of hydrogen ion, that's proton. So how you form conjugate acid is by addition of hydrogen ion that is proton also. So weak acid and conjugate base will form an acidic buffer, and then weak base and conjugate acid will form a basic buffer. So let us see an example of an acidic buffer here. Weak acid, an example of weak acid is, let's use ethanoic acid, is CH3COOH. So this is ethanoic acid, and the conjugate base is formed by the removal of the hydrogen ion. So this is the conjugate base, CH3COO minus. So this is an example for an acidic buffer. While for a basic buffer, an example of a weak base is NH3. That's ammonia. That's an example of a weak base. And then the conjugate acid is going to be NH4 plus. So that's by addition of a hydrogen ion. So this is an example of an acidic buffer, an example of a basic buffer. So for the blood, the pH of the blood, as you can find in your material, is 7.35. And the buffer, the significant buffer in the blood happens to be hydrogen triazocarbonate 4, that's H2CO3, and then this is the conjugate HCO3 minus. So for us to calculate the pH of buffers, there are two formulas here according to Hasselbalch equation. So the pH for weak acid / conjugate base is equal to pKa plus log concentration of salt. Whenever you see square brackets in chemistry, it simply means concentration. Concentration of salt over concentration of acid. While for weak base conjugate acid, we have POH, please take note of that, equal to pKb plus log concentration of salt over concentration of base. This is a rectangular bracket. So when you are working with weak as basic buffers, use this formula, and then when you get your POH, you simply do 14 minus POH for you to get your pH. When you are working with acidic buffers, use this particular formula, and then you get your pH straight up. So let us walk through some examples, and we can make progress in this particular tutorial. So first example says calculate the pH of a buffer solution containing 0.2 mole of NH4Cl and 0.1 mole of NH4OH per liter. That means what we have for ammonium chloride, ammonium is like this, shows ammonium chloride and then ammonium hydroxide. Now this shows you a base, that's a weak base, and then this shows you the conjugates. So this is the salt and this is the base. So what we're going to use for calculating this is going to be this particular formula. And then they already told you 0.2 mole per liter. That's actually 0.2 mole per dmq. And then 0.1 mole per liter, that's 0.1 mole per dmq. So let us solve for this very quickly without wasting so much time. Meanwhile, they gave us the Kb of the dissociation constant of the base as 1.85 times 10 raised to the power of minus 5. And we have mentioned earlier on that whenever you have pKb is equal to negative log of the hydroxide ion concentration. So that's going to be negative log of Kb, so that's going to be minus log of 1.85 times 10 raised to the power of minus 5. So if we press that in our calculator, we're going to have this right away. So that's minus log 1.85 times 10 raised to the power of minus 5. So that's going to give us a value of 4.73. So this is our pKb. And then we can now go ahead and do our complete solving. So what we have here is this. POH is equal to pKb. What is pKb? 4.73, as we have calculated from the Kb that was given to us. And then plus log concentration of the salt. The salt here happens to be ammonium chloride. So it's 0.2 mole per dm cube. So that's going to be 0.2. And then the concentration of the base. The base here is ammonium hydroxide. And that's 0.1 mole of ammonium hydroxide per liter. So that's going to be divided by 0.1. So our POH is equal to 4.73 plus 0.2 divided by 0.1 is going to give us 2, and then log of 2 is going to give us 0.3010. 0.3010. So our POH is equal to 4.73 plus 0.3010, and that's going to give us 5.030 1. Meanwhile, our question says calculate the pH. And what we have from the Henderson-Hasselbalch equation is pOH. So for us to get the pH, we know that pH plus pOH is equal to 14. So it simply means that our pH is equal to 14 minus pOH, which we now make 14 minus 5.031. So the pH for this particular buffer solution is then going to be 8.969. So 8.969 is going to be the concentration of this buffer solution which we just calculated for. And that is how you work around calculation of the pH of a buffer solution using Henderson-Hasselbalch equation. So let us look at example number 2 and then let us walk through it also. It says a buffer solution was made by dissolving 10 grams of sodium acetate, which has a molar mass of 82 grams per mole, in 200 ml of 1.00 mole per dm cube acetic acid. What we have here is a weak acid alongside its conjugate base or its salt, sodium acetate. Assuming that the change in volume when the sodium acetate was added is not significant, what it means is that there's no dilution in this particular context, estimates the pH of the buffer solution. The Ka for the acetic acid is 1.7 times 10 raised to the power of minus 5. So when you see questions like this, first thing to do is to identify what kind of buffer solutions do we have. When you know the buffer solution we have, automatically you know which of the Henderson-Hasselbalch equation you are supposed to employ for the particular solution. So for this particular solution, we have acetic acid and then sodium acetate. It tells us a weak acid and its conjugate base. So we use the formula for pH directly. So let us see what that is going to look like. So let me divide this for us to get our solution. Now we know, according to the formula, we need pKa. So let us solve for pKa. We have been given Ka and we know that pKa is equal to negative log of Ka. So what is that? That's going to be minus log of 1.7 times 10 raised to the power of minus 5. So our pKa is equal to minus log of, our pKa is minus log of 1.7 times 10 raised to the power of minus 5. And that's going to give us 4.7695. So that's approximately 4.77. That's approximately 4.77. The next thing we need, according to the Henderson-Hasselbalch equation, we're going to need the concentration of the salt. Now the salt here we have here is sodium acetate, and it said 10 grams of sodium acetate is dissolved in 200 ml of a 1.00 mole per dm cube of acetic acid. So let us focus on the salt first. Sodium acetate 10 grams is dissolved in 1 mole per dm cube of acetic acid. Now we know that 10 grams of sodium acetate is used, but according to the molar mass, we know that for the molar mass, 82 grams of sodium acetate is going to represent 1 mole of sodium acetate. Let me explain that. Now, sodium acetate is what is the salt. Acetate, that is the salt. Based on the molar mass, 82 grams per mole simply means that 82 grams is present in 1 mole. But then what was used is 10 grams. So 10 grams is going to make up X mole. How do we calculate for X? We simply cross multiply and then we divide. That is this times this times this divided by 82. So we're going to have that our S mole is equal to 10 times 1 divided by 82. 10 times 1 divided by 82. So and that's going to give us 0.122 moles. So the amount of salt we have, sodium acetate is 0.122 mole. What it means is that 10 grams of sodium acetate is actually 0.122 mole of sodium acetate. Then let us check the amount of acetic acid we have there. The acetic acid we have there, so let's look for acetic acid, and that is like the weak acid. That's the weak acid. According to this, it says that 200 ml of 1.00 mole per dm cube of acetic acid. We are aware that 1000 ml is equal to 1 dm cube. We are aware that 1000 ml is equal to 1 dm cube. And when it says 200 ml of 1 mole per dm cube, 1 mole per dm cube simply means that 1 mole is present in 1000 ml of acetic acid. It simply means that 1 mole is present in 1000 ml of acetic acid. Why did I say 1000 ml? Because we are aware that 1 dm cube is equivalent to 1000 ml. But then it is not 1000 ml that was used. What was used was 200 ml. So if 1 mole is present in 1000 ml, X mole will now be present in 200 ml. We want to know the amount that is present in 200 ml. How do we do that? We simply cross multiply and we divide. So our X mole for the acid is going to be 1 times 200 divided by 1000. So we have 1 times 200 divided by 1000. So that's going to be 200 divided by 1000, and that's going to give us 0.2 mole. So we already have the amount of the acid as 0.2 mole and the amount of the salt as 0.122 mole. And we already have our pKa as 4.77. The next thing to do is to apply the Anderson-Hasselbalch equation and then get the pH of this particular solution, because it says estimate the pH of the buffer solution. So our pH is equal to pKa is 4.77 plus log concentration of the salt, we have 0.122 divided by, then the amount for the acid is going to be 0.2 as calculated. Our pH is now equal to 4.77 plus 0.122 divided by 0.2. And then the logarithm of that value is going to give us plus in brackets minus 0.2147. So our pH is now equal to 4.77 minus plus times minus will give us minus 4.77 minus 0.2147. That's going to give us 4.5553. So our pH is approximately 4.56. So the pH of the buffer solution formed between acetic acid and sodium acetate, according to the amounts that are given here, is going to be equal to 4.56. We're not going to be using these because we know that this is pH directly. Meanwhile, when you're working with weak base and conjugate acid, you work for pOH and then use 14 minus pOH for you to get the pH directly. So let us look at our last example for this particular aspect of calculating the pH of buffers using the Anderson-Hasselbalch equation, so I can be able to gain more insight. Meanwhile, this one is not going to use that particular equation. It's something that is very, very unique, because this time around they're not asking us to look for the pH. What we are asked to look for is the ratio. Calculate the ratio of ammonium chloride to ammonia. What is it telling you? That what we have here is a buffer solution, a basic buffer that is formed between a weak base and then its conjugate acid. So ammonium chloride to ammonia, that is required to make a buffer solution with a pH of 9.00. The Ka for ammonium ion is 5.6 times 10 raised to the power of minus 10. So for us to be able to calculate this, we need to work on the dissociation of the ammonium ion. We're going to work on the dissociation of the ammonium ion. It said the ratio of ammonium chloride to ammonia that is required to make a buffer solution with a pH of 9.00. The Ka for ammonium ion is 5.6 times 10 raised to the power of minus 10. So let us work on the dissociation of the ammonium ion so we can be able to make progress in that regard. Now, ammonium ion, NH4 plus, in the presence of water, is going to dissociate to give us H3O plus NH3. So ammonium ion in the presence of water is going to dissociate to give us H3O plus NH3. So this is our ammonium ion and this is our ammonia in a state of change in the solution. Are we together now? So based on this, we can be able to calculate that ratio that they want us to calculate. How? We know that when you want to calculate for dissociation constant, which is K is equal to the concentration of products, multiplication of product divided by the concentration of the multiplication of the reactant. How do I mean? We know that Ka is equal to products, concentration of the product. So we have H3O plus and then multiplied by concentration of ammonia divided by the concentration of the reactant. So we have NH4 plus. Now we are supposed to add hydrogen and water to it, but I've already explained prior to this time that when you have to deal with water, because of the insignificant change you have in that concentration, it is not usually factored into the calculation of dissociation constant. Refer back to the beginning of this video so you can make you can have appropriate understanding of why water is not usually used when we are calculating dissociation constant. I already explained that at the beginning of the video. So we're not going to add water to it, we're just going to work with this. So we have that Ka is equal to H3O plus then times NH3, concentration of NH3 and then concentration of the ammonium ion. Now let us look at this very clearly. What we are asked to look for is the ratio of ammonium chloride to ammonia. So what it simply means that we need to look for the ratio of the concentration of the ammonium ion to the ammonia that is in this solution. So let us make that ratio a subject of formula. Can we do that? Yes, we can do that. Ka times concentration of ammonium ion is equal to concentration of H3O plus times concentration of ammonia. So in looking at this now, what it simply means that we can divide both sides by an NH3, and then we now have NH4 plus divided by NH3, which is the ratio of ammonium chloride to the ammonia. Then we can now divide both sides by Ka for us to have this divided by Ka. So I think for the purpose of this video, so I will not be too fast, let me take it step by step. So first thing first, we'll divide both sides by NH3. So I'm going to divide both sides by concentration of NH3. So I'm going to divide both sides by the concentration of NH3. So when we do that, this will cancel out this. So what we now have left will be Ka times concentration of ammonium ion divided by NH3 is equal to the concentration of the hydrozonium ion or the ozonium ion. Now the next thing we're going to do to take Ka from here to this place is to divide both sides by Ka. If you're going to be dividing both sides by Ka, you can do the maths. If you do division here, that's Ka times NH4 plus divided by NH3 plus. Okay, let me do the calculation so I can get it, so you don't get confused at that point of the calculation. So Ka times NH4 plus divided by NH3. We want to divide by Ka, so we're going to do divided by Ka. Now, you know in your preliminary mathematics that when you have anything you are dividing, if you are going to convert the divide to plus, you simply do the reciprocal. So you reciprocate. So if I'm going to change this division to multiplication, I will simply reciprocate the Ka. So if I'm going to change that, I'm going to have this times 1 over Ka. So this thing and the other one is also the same thing. So that's what you do in your basic mathematics. Now that we now have times 1 over Ka, this Ka cannot cancel this Ka. So all we now have left will be NH4 plus divided by NH3. Now we already have the ratio of ammonium chloride to ammonia. This is what we are looking for. Now that we have that ratio, and then for you to divide it, you just simply do this divided by Ka. So all we now have at the end of the day is going to be NH4 plus divided by NH3. NH3 is equal to H3O plus divided by Ka, because we are dividing both sides by Ka. Now, what is our Ka? We have Ka 5.6 times 10 to the power of minus 10. But we need to know the concentration of the hydrogen ion. How do we get that? Yes, we can get that because we are given the pH of the solution. pH of 9.00. Now we know how to calculate pH. So I'll calculate the pH here, and then we'll pick up the value, and then we use that to solve very clearly. So we know that pH is equal to negative logarithm of hydrogen ion concentration, and you know that you can actually use hydrogen ion concentration, or also you can also use the hydrozonium or ozonium ion concentration. They are the same thing. Just like in this one, water is factored into this particular stuff. So let us solve. Now that we know pH, we can actually get this. How do we get that? We simply make it a subject of formula. So H3O plus is now equal to antilog of negative pH. Antilog of negative pH. So that's going to be antilog of minus 9.00. So that is going to give us the hydrogen ion concentration. So we simply do antilog of minus 9.00, and that's going to give us 1 times 10 raised to the power of minus 9. So this is the concentration of the hydrogen ion in this particular formula. So can we fix that? Yes. Yeah, we can fix it here. So we now have 1 times 10 raised to the power of minus 9 divided by, what's our Ka? 5.6 times 10 raised to the power of minus 10. So can we now make this in ratio format? This is now going to be divided by 5.6 times 10 raised to the power of minus 10. Alright, so this is now going to give us 1.7857 divided by 1. So we have NH4 plus divided by NH3. And the question says, calculate the ratio of ammonium chloride to ammonia that is required to make a buffer solution with a pH of 9.00. This is ammonium chloride, the representation here, and then this is the ammonia. This ratio is equal to this ratio. So what it simply means is that 1.7857 amount of ammonium chloride will be necessary to react with 1 of ammonia to form a buffer solution that has a pH of 9.00. So if you are thinking in terms of amount, this is like, you can say this is 1.7857 mole per dm cube divided by 1 mole per dm cube of ammonia. So this is how you calculate for the ratio of ammonium chloride to ammonia. So when we talk about buffers, there's something we call buffer action. Buffer action actually talks about the ability of a buffer solution to be able to resist changes in pH on the addition of small amounts of acids or bases to it. And the buffer action is usually due to the reserved acidity or the reserved basicity that is found in that particular solution. So moving ahead, we are going to talk about buffer capacity and how to use the formula for buffer capacity to calculate buffer capacity, and then we're going to look at other areas of this particular course. So let's make progress. All right, so we are done with talking about buffer solution. We're talking about buffer action. What we're going to be talking about is buffer capacity. When we talk about buffer capacity, we are talking about the number of moles per liter of acid or base that you need to add to a particular solution to cause an increase or decrease by 1 pH unit in that solution. So buffer capacity simply refers to the number of moles of acid or base per liter that is necessary to be added to a particular solution to cause an increase or decrease of 1 pH unit in that particular solution. So let's assume that the solution has a pH of, let's say, 5. For you to increase the pH to 6, or for you to decrease the pH to 5, that's by 1 unit by 1 unit. That's what we refer to as the buffer capacity, the amount of acid or base that will be necessary for you to do that. For a solution to have a good buffer capacity, you need to have the acid being ionized at 50%. What it simply means that the concentration of the salt and the concentration of the acid should be as close to 1 as possible. More details can be found in your material. Meanwhile, in this particular tutorial, we will look at the basics of the calculations, so you can be able to tackle any problem that comes in that direction. So buffer capacity, we have two formulas here. The first formula says that buffer capacity is equal to number of moles of acid or base added to 1 liter divided by change in pH. Change in pH will simply means that you are subtracting the pH before and the pH after, depending on which one is larger in the pH value. So you do the subtraction and then you get the change in pH. Another formula is buffer capacity is equal to 2.03 times C times Ka times H3O plus concentration divided by Ka plus H3O plus concentration, all in brackets raised to the power of 2. What is C in this calculation? C equals to the total buffer concentration, and the total buffer concentration is the sum of the concentration of the buffer components in molarity. In molarity tells you that this is in mole per dm cube. So the concentration must be in mole per dm cube. That's what the molarity is telling you. And then the sum of the concentration of buffer components. We already told you that buffers are made up of acid with conjugate base or base with conjugate acid. So if you are having acid plus conjugate base, it means that the total buffer concentration will be the concentration of the acid plus the concentration of the salts. If it is base and conjugate acid, it will be total buffer concentration is equal to the concentration of the base plus the salt. So that's why you have A or B. So it's either concentration of acid plus the salt or concentration of the base plus the salt, which represents the conjugates. So let us look at we'll look at 3 examples. We'll look at the 4th example, and from there we'll move over to solubility product, common ion effect, and then we'll solve the exercise at the back of the tutorial materials. At any point where you get confused, please do well to ask your questions in the comment section, and it will be attended to promptly by the academic committee of the National Fellowship of Christian Pharmacy Students, UNN chapter. So we have a buffer solution has an amount of acid with 0.02 mole. 0.02 mole. Initial and final pH is 4.75 and 5.20 respectively. The question says find B. Beta simply means buffer capacity. So which formula are we going to use? We are going to use the first formula because we already have the amount of acid, and then we have the change in pH. So our buffer capacity, beta, is equal to number of moles of acid is 0.02. Our change in pH is going to be 5.20 minus 4.75. Like I told you, change in pH is simply do the subtraction of both the initial and the final. Anyone that is bigger comes first, and the one that is smaller comes second, irrespective of whether it's the initial or the final. What we need is change in pH. So we have 0.02 divided by 5.20 minus 4.75. So 5.20 minus 4.75, that's going to give us 0.02 divided by 0.45. So 0.02 divided by this answer is going to give us 0.044. Yeah, 0.0044. So let us be sure of what we calculated. Let's be sure of what we calculated. So 0.02 divided by this answer is going to give us 0.044. So that's the buffer capacity for that solution. Let's look at another question. It says calculate the buffer capacity of a solution composed of 0.2 mole per dm cube of acetic acid, that is an acid, and 0.2 mole per dm cube of sodium acetate, that is the salt of the acid. So this buffer solution is an acidic buffer made up of the acid and the conjugate base as the salt sodium acetate at a pH of 4.76. Now we are having the acid concentration and the salt concentration. The formula that comes to mind is this formula that has total buffer concentration for you to work with. So we can get the total buffer concentration and also the concentration of the hydrozonium ion. So let us start with the total buffer concentration. Total buffer concentration, C is equal to the Ca plus Cs. What is Ca? Ca is the concentration of the acid, which is 0.2, and Cs is the concentration of the salt, which is 0.2. 0.2 plus 0.2 will give us 0.4 mole per dm cube. 0.4 mole per dm cube. So the next thing we need to calculate is for the concentration of the hydrozonium ion. We are aware that pH is equal to negative logarithm of H plus ion. And I've told you before that this thing is same thing as negative logarithm of hydrozonium ion, because in hydrozonium ion you just factor in the water in there. How do I mean? For hydrozonium ion is simply H2O plus H plus. That's what gives us hydrozonium ion. So it is still this hydrogen that is still functioning in that regard. So this is same thing as this. So if this is same thing as this, and we are told that the pH is 4.76, it simply means that 4.76 is equal to negative logarithm of H3O plus. So can we get the concentration of hydrogen, hydrozonium ion? We can get that. So our hydrozonium ion, H3O plus, is now equal to our antilog of minus 4.76. Antilog of minus 4.76. So antilog of minus 4.76 is going to give us 1.737. Let's make it 1.738 times 10 raised to the power of minus 5. 1.738 times 10 raised to the power of minus 5. That's the concentration of the hydrozonium ion. So we can now calculate for our buffer capacity. Our buffer capacity is equal to 2.303 times our C. What's our C? 0.4. So that is 0.4 times, what's our Ka? Our Ka is 1.75 times 10 raised to the power of minus 5, and then times, what's our hydrogen ion concentration? That will be 1.738 times 10 raised to the power of minus 5, and this is divided by in brackets, open bracket, 1.75 times 10 raised to the power of minus 5 plus 1.738 times 10 raised to the power of minus 5, close bracket, everything raised to the power of 2. So let us calculate our buffer concentration quickly. So we're going to have 2.303 times 0.4 times 1.75 times 10 raised to the power of minus 5 in bracket times in bracket 1.738 times 10 raised to the power of minus 5. So the numerator is equal to 2.8018 times 10 raised to the power of minus 10 divided by, let us get the denominator. Let us get our denominator. So we have 1.75 times 10 raised to the power of minus 5 all in brackets plus 1.738 times 10 raised to the power of minus 5 all in brackets, and then we have square of that answer. That square is going to give us 1.2166 times 10 raised to the power of minus 9. So in bracket 2.8018 times 10 raised to the power of minus 10 divided by in brackets 1.2166 times 10 raised to the power of minus 9 is going to give us our final answer, which is 0.23. So our buffer capacity for this particular solution is going to be 0.23. So very simple stuff. Know how to use your formula, apply it, and you get your answer. So let us look at the third example before we look at the last example, and then move over to solubility product, common ion effect, and then we solve the exercises. So we have 50 ml of 0.1 mole per dm cube HCl was added to a buffer consisting of 0.025 moles of sodium acetate and 0.030 moles of acetic acid. So this is an acidic buffer made up of acetic acid and its conjugate base, which is the sodium acetate salt. What is the pH of the buffer after the addition of the acid? Ka of acetic acid is 1.7 times 10 raised to the power of minus 5. Then the next thing is calculate the buffer capacity. So we have two questions. First question is to know the pH after the addition of the acid, and then we'll now calculate the buffer capacity. Now I want you to pay attention to this very carefully. I'm going to be taking it step by step so you can understand how to use the ICE table and be able to get your answers accordingly. Now let us divide this for the want of space in this particular explanation for this particular question. So let us look at this. Let us look at the reaction, the dissociation of acetic acid. Let's look at the dissociation of the acetic acid. We have CH3COOH, we have CH3COOH plus H2O dissociating into CH3COO minus plus H3O plus. So dissociating into CH3COO minus plus H3O plus. And based on this is a 1:1:1:1 equation. So this is a 1:1:1 equation. What does that simply mean? That simply means that 1 mole of acetic acid in 1 mole of water will give 1 mole of acetate, that's ethanoate, and then 1 mole of hydrozonium ion. Now, why is it important for us to write this out? It is important because of this. If you are adding an acid, to this particular buffer, what you are going to be doing is that acid is going to cause this to continue to react with hydrozonium ion and produce more of CH3CO. This is Le Chatelier's principle. The reaction is going to shift towards the left because of the addition of acid. You are increasing the amount of H3O plus. So for it to be balanced, more of this will react with this to be converted to the acetic acid. Meanwhile, if you are adding base, base is going to be causing more of this to be released and converted to this. So it's something you have to understand very clearly. This first example captures acid. The second example will capture base. And then when we solve maybe 1 or 2 exercises, you will to get that very clearly. So the first thing we have to do is that we'll calculate the pH before the addition of the acid. How do we calculate the pH before the addition of the acid? According to Henderson-Hasselbalch equation, we know that the pH is equal to the pKa. The pH is equal to the pKa plus log salt over acid. The pH is equal to the pKa plus log salt over acid according to the Henderson-Hasselbalch equation. So let us now calculate. Our pKa, we are given that the Ka of acetic acid is 1.7 times 10 to the power of minus 5. And we know that pKa is equal to minus log of Ka. What is Ka? 1.7 times 10 to the power of minus 5. So we simply do minus log open bracket 1.7 times 10 to the power of minus 5. And that's going to give us 4.7695. And that's approximately 4.77. That's the pKa. Then the next thing we need for this equation is the concentration of the salt. Concentration of the salt is 0.025. Concentration of the acetic acid is 0.03. So can we now be able to calculate for the pH? Yes, we can. Our pH will now be equal to 4.77 plus log 0.025 divided by 0.030. So our pH is equal to 0.025 divided by 0.03. And then the logarithm of that is going to be a minus. Minus times plus will give us minus. So that's 4.77 minus 0.0792. So our pH is equal to 4.77 minus 0.0792. And that's going to give us 4.6908, which is approximately 4.69. So the pH before the addition of the acid is going to be 4.69. And as you already know, addition of the acid will most likely cause the pH to reduce further. But nevertheless, let us work with the tables that are going to help us in getting our values right. Now, the next thing we have to know is about the acid. The acid that was added, we needed to know how many moles of HCl was actually added to cause whatever change that occurred here. We were told that 50 ml of HCl of 0.1 mole per dm cube of HCl was responsible for that conversion. So let me give you a formula that you need to remember here. Number of moles is equal to volume in dm cube times concentration in mole per dm cube. So number of moles, which is moles, is equal to volume in dm cube. The unit for this, that's mole, is equal to volume in dm cube times concentration in mole per dm cube. So we have 50 ml. How do we convert 50 ml to dm cube? We are aware that 1000 ml is equal to 1 dm cube. So 50 ml will now be equal to what? 50 divided by 1000. So the number of moles of HCl that was added is now equal to 50 divided by 1000, that's the volume in dm cube, times the concentration. Our concentration is 0.1. So we simply do 50 divided by 1000 times 0.1. And that's going to give us our number of moles of HCl added is now equal to 0.005 moles. So we have 0.005 moles as 1, 2, 3. Yeah, 0.05 moles of HCl has been added. So the next thing we're going to do now is for us to draw the ICE table. We're going to be drawing the ICE table so that you can be able to see how you can feature that in the ICE table and come up with your pH after the addition of the acid. So let us draw the ICE table quickly. So for the ICE table, what we're going to have here, we'll have our initial amount. Then we're going to have our change in amounts, and then we're going to have our equilibrium amount. So we have our initial amount, our change in amounts, and then we're going to have our equilibrium amount. That is where they got the name ICE table from. So this is ICE. Once you remember ICE, what comes to your mind is initial amount, change in amount, and equilibrium amount. So the next thing we're going to be featuring here, we're going to be featuring the respective compounds that are necessary for this calculation. So we have CH3COOH, we have CH3COOH, we have H3O plus, and then we have CH3COO minus. Now I told you this is the conjugate base which represents the sodium acetate we have there, which is the salt. And then this is our acetic acid, and this is the hydrogen ion concentration. Now the initial amount, what's the initial amount of acetic acid? The initial amount of acetic acid here is 0.03 moles. So we have 0.030 moles. What's the initial amount of the conjugate base? That's the salt, sodium acetate. What we have there is 0.025 moles. What about the hydrogen ion concentration? For us to know the original amount of hydrogen ion concentration, we will simply have to do the antilog of the negative value of this. Since pH, initial pH is 4.69, and we know that pH is equal to negative logarithm of hydrozonium ion concentration. For us to get the hydrozonium ion concentration, we simply do the antilog of the negative of this. But then we don't need that. Why don't we need that? We don't need that because what we are simply dealing with is the amount of HCl that is added. And we know that when HCl is added in the presence of water, what is going to be released is going to be H3O plus Cl minus. H3O plus Cl minus. So what it means is that there will be addition of what? H3O plus in the solution. And this equation is a 1:1:1 equation. What it simply means is that 1 mole of HCl will produce 1 mole of hydrozonium ion. But according to our calculation, we have 0.05 moles of HCl. If 1 mole of HCl will give 1 mole of hydrozonium ion, it simply means that 0.005 moles of HCl will also give us 0.005 moles of hydrozonium ion. So the initial amount of hydrozonium ion that is deposited by the HCl is going to be 0.005. I hope it's making sense. So if you are getting confused, slow down, take it back, and then watch it again. So let us go to the change in amounts. When we add more H3O plus, according to Le Chatelain principle, for the purpose of balance, this reaction will shift towards the left because more of this will react with this compound to form more of this. So what it means that this is going to increase, but this is going to decrease alongside this. So what we're going to have here is that H3O plus will react with this for it to give this. And this is also a 1:1 reaction. So what it means is that 1 mole of this reacts with 1 mole of this to give 1 mole of this. So we are going to be working with same ratios. So since we have 0.005 of H3O plus and we have 0.025, this one is higher than this. So the limiting reactant here happens to be H3O plus. This one will finish before this is finished. So this is our limiting reactant. So it will determine the amount of this that is produced. So 0.05 will be used up. So the change in amount now is minus 0.005. That will change in amount. And then the amount that will be used up here automatically will also be minus 0.005 because this will react with this, thereby decreasing the amount of the conjugate base that is available. Meanwhile, this guy is going to increase by 1 also, so we're going to have plus 0.005. So let me explain again. H3O plus, because it is donated by HCl, according to that equation, when it increases, it will have to react with this to move the reaction to the left, so that this is going to increase and then it will come down. So the H3O plus that is added is 0.05. It will react with 0.005 of CH3COOH to give us 0.005 of the acetic acid. So the next thing to now calculate is the equilibrium amount. So 0.030 plus 0.05 is going to give us 0.035. If you add this, it's going to give you 0. Now, if you look at your material says X. Why is your material saying X? Your material is saying X because, like I told you earlier on, we did not find the value of the hydrogen ion concentration before you added the acid. So when they work with the S, what they're going to do is that they will use that particular X to now get the pH directly. But instead of us to go through that long process, what we'll simply do is that we'll still work with our concentration of salt and acid using Henderson-Hasselbalch equation, and we'll still get the same answer. You have the material in front of you. When we solve with the Henderson-Hasselbalch equation, you will see we are getting the same thing. And this is a way simpler way to go rather than going through that complex way of having X here. So let us go here. So this minus this will give us 0. And then for this, 0.025 minus 0.005 is going to give us 0.020. So now we have a higher amount of acetic acid and a lesser amount of our conjugate base / salts. So can we now get the pH after the addition of the acid? Yes, we can get it. Our pH is now equal to, what's our pKa? Our pKa is the same thing, which is 4.77 plus log salt. Our salt now is now going to be 0.020 divided by our acid. Our acid is going to be 0.035. Our acid is going to be 0.035. So that will be 4.77. And then let's do our log. 0.020 divided by 0.035. And then the logarithm of that is going to be minus 0.2430. Now, minus times plus will give us minus. So that will be minus 0.2430. So our pH is now equal to 4.77 minus 0.2430. That's going to give us 4.527. So that's approximately 4.53. So if you check your material, you see that what we have there with the other procedure is same thing. Now, do you remember what I told you? By addition of acid, we are going to be causing the pH to go down. So 4.69 initially, when you added acid, the pH dropped down to 4.53. So I just solved one part of the question. The second part of the question says, calculate the buffer capacity. What is the buffer capacity? The buffer capacity is referred to as the amount or the number of moles of acid or base added. What is the amount of acid added? 0.005. That is 0.005 divided by the change in pH. What is change in pH? You are simply subtracting initial and final. So what you have here is 4.69. Since 4.69 is bigger, so you have 4.69 minus 4.53. So what you're going to have there is 4.69 minus 4.53. That's going to give us 0.16. So 0.005 divided by 0.16 is going to give us a buffer capacity of 0.03125. And you can approximate it to 0.032. 0.31. So this is the buffer capacity for the solution, and this is the pH after the solution. So we're going to look at a second example on this kind of question, and then by that second example you should be able to understand how to use the ICE table, and then we'll make progress to solubility product, and then we'll do other things. Alright, so we're going to be doing the last example under buffer capacity, and I'll be showing you how to work with the ICE table one more time. Then from there we'll progress to solubility product, we do common ion effect, and then we are going to solve some of the exercises, and the reminder you can find it in the document that's attached to the link in the description below for this particular video. So we're going to be working with number 4 question. It says calculate the change in pH of a solution composed from 0.010 mole per dm cube acetic acid with a pKa of 4.76 and 0.028 mole per dm cube sodium acetate after it is neutralized with 10 ml or 0.1 mole per dm cube NaOH, assuming no significant change in volume after neutralization. Then calculate this buffer capacity. So I calculate for two things: the change in pH and then the buffer capacity. So the first thing for us to run here is to write the dissociation equation. So what we have here is CH3COOH with water dissociating into CH3COO minus plus H3O plus, a 1:1 equation. So that's what we have there. So the first thing we're going to do, as always, is to calculate the pH, initial pH of the equation. So let us calculate the initial pH for this particular solution. So we're going to calculate the initial pH. And then we're going to work with the ICE table. So we say pH is equal to pKa plus log salt over acid. So our pH is equal to pKa, according to this, is 4.76, and then log, what's the concentration of the salt? The salt is 0.028, and then the acid is 0.01, so that's 0.010. So our pH is equal to 4.76, so that's 0.028 divided by 0.01, and then the logarithm of the answer, we're going to have plus 0.4472. So our pH is equal to 4.76 plus 0.4472. That's going to give us 5.2072, which is approximately 5.21. So our pH is 5.21. And then the question says we should calculate the change in pH of solution when it is neutralized with 10 ml or 0.1 mole per dm cube. So this particular one is capturing a neutralization reaction that is occurring due to the addition of sodium hydroxide. So let us calculate the number of moles of sodium hydroxide that is being added. We know that number of moles is equal to volume in dm cube times concentration in mole per dm cube times concentration in mole per dm cube. So we're going to be doing the volume in dm cube. The volume is given as 10 ml. To convert to dm cube, we divide by 1000. So we have number of moles of NaOH, that's 10 divided by 1000, times the concentration, which is already in mole per dm cube, times 0.1. So we're going to be having 10 divided by 1000 times 0.1. That's going to give us 0.001 mole of NaOH. So 0.001 mole of NaOH was what was added to the solution. So the next thing for us to do is for us to draw our ICE table. So let us draw our ICE table, and then we are going to make progress. So this is our ICE table right here. So as always, we have our initial amount. We have our change in amount, and then we have equilibrium amounts. So we have equilibrium amounts, and then we have the compounds we are working with. We have the compounds we are working with. We have CH3COOH. We have CH3COOH. Then we have our CH3COO minus, which is the conjugate base / salt. But the only thing now we are not going to consider is if we are going to be using H3O plus in the middle, or if we are going to be using NaOH in the middle. Now there's something I need to get clear for you. Now in the former example, what was added was an acid. So what was increasing was the ozonium ion. The ozonium ion was what was increased by the addition of that acid, thereby shifting the reaction to the right. But this time around, what is being added is not an acid. What is being added is a base, and that base is NaOH. So let me show you something. When you add NaOH, what is going to happen is that CH3COO minus plus NaOH is going to move the reaction to CH, it's going to move the reaction to CH3COO Na plus OH minus. All right, so it's going to move the reaction to, this is COOH, COOH is going to move this to CH3COO plus H2O. So what we have here is the addition of a base, and the question already gave us a hint that it's a neutralization reaction. So when you have a base added, the base will react with the acid. What is the acid? The acetic acid, and then it's going to lead to a formation of the CH3COOH plus H2O as water. Now we already know that what we have here, this is the conjugate, or this is the salt, which when it dissociates to give you the conjugate base. What is the conjugate base? Conjugate base is CH3COO minus, and then you have the Na plus. And I already told you that the Na plus do not play any role in the change of pH, because that's the cation of a strong base. So this is what is being formed in essence. I don't know if you're getting it now. So an addition of NaOH, this is going to decrease while this is going to increase, because the base will neutralize the acid to produce more of the salt, which will form the conjugate base. So what we're going to add here, if you're adding H3O plus, it is not going to be necessary because there's no increase in H3O plus. But what you can be able to add here, if you're going to add H3O plus, you have to be writing not needed in the spaces provided. But if you don't want to add H3O plus, you can simply add your NaOH. In the material, what we have there is H3O plus, but you see not needed because it's not necessary. But we're going to be working with NaOH, so I can see realistically how these values apply in the ICE table. So the initial amount of the acetic acid, according to our question, is 0.010. The initial amount of sodium hydroxide that was added was 0.001, and the initial amount of the sodium acetate that was present was 0.028. Now, this is going to react with this. This is going to react with this to produce more of this, which is going to form our conjugate base. So what it simply means that this will go down, and this is going to increase. Now, between this value and this value, this is going to be the least, and it means that it's the limiting reactants. So what we're going to have here is minus 0.01, minus 0.001, and then you're going to have plus 0.001 because this is going to increase. So when we do that, we simply do 0.01 minus 0.001, and that's going to give us 0.009. And then for this will give us 0, and then 0.028 plus 0.001, that's going to give us 0.029. So the amount of the salt has increased while the amount of the acid have decreased because of the presence of a base that neutralized this solution, So we're going to calculate the new pH now. The pH is now equal to pKa, which is 4.76 as given to us, plus log salt. Salt is now 0.029 divided by acid, which is 0.009, and then our pH, because we are adding a base, the pH has to increase, so we can predict and know where we are going to in this particular calculation. So this is 4.76 plus 0.029 divided by 0.009, and then you have the logarithm of this answer plus 0.5082. So our pH is now going to be equal to 4.76 plus 0.5082 is going to give us 5.2682, which is approximately 5.27. So the original pH initially was 5.21, and now the pH is now 5.27 because addition of the base increased the pH. So the question says calculate the change in pH. So the change in pH is equal to 5.27 minus 5.21. So we're going to have 5.27 minus 5.21, and that's going to give us 0.06. That's the change in pH. Second question says calculate the buffer capacity. Our buffer capacity is equal to the number of moles of acid or base that is added, and the base that is added is 0.001 divided by change in pH. I've already calculated the change in pH to be 0.06. So our buffer capacity will now be 0.001 divided by 0.06, and it's going to give us 0.0167 as our buffer capacity. So this is as clear as possible in terms of calculation using the ICE table: initial amount, change in amount, and equilibrium amount. So the next thing we're going to be moving over to is the solubility product. Solubility product of a sparingly soluble salt AXBY is given as KSP, solubility product, equal to S to the power of S plus Y dot, that's multiplied by S to the power of X multiplied by Y to the power of Y, where X represents the solubility. Another formula you can want to use is for MPXQ, KSP is equal to the concentration of M plus, that's when it's dissociated, raised to the power of the what you have at the base, and then the concentration of the S minus raised to the power of what you have at the base there, which is the Q. So what we're going to be working with now, we'll do a few examples, 1, 2, 3, and then we're going to go over to common ion effect. So the first one says, what is the solubility of silver chloride in water, given that pKsP is equal to 9.75? What is the solubility of silver chloride? So silver, what we have at the denominator, what we have here is 1, and then for the Cl, the subscript you have for Cl is 1. So the coefficients are 1. So for us to be able to calculate this, it says pKsP. Anyway, we see P in this format, we know what it simply means is negative log of KSP. So if pKsP is equal to 9.75, and we know that pKsP is equal to negative logarithm of KSP. Negative logarithm of KSP. So can we be able to get KSP? Yes, we can make KSP a sort of formula. So KSP will now be equal to antilog of negative pKsP. And what is that? That's going to be antilog of negative 9.75. Antilog of negative 9.75. So that's minus 9.75, and that's going to give us 1.78 times 10 raised to the power of minus 10. So that's our KSP. Our KSP is now 1.78 times 10 raised to the power of minus 10. And then we can now calculate for the solubility product. KSP, okay, we are now asked for solubility product, but let us write the formula for solubility product. KSP is equal to X, which is solubility raised to the power of, for silver chloride, what is subscript is 1, So our X is equal to 1, which is our X here, and our Y will be equal to 1. Then this will be dot 1 raised to the power of 1, dot 1 raised to the power of 1, because the subscript for both of them is 1, 1. So we're going to have this. When you work on this, this is going to give you 1 raised to the power of 1 is 1, 1 raised to the power of 1 is 1, and then you have S 1 plus 1 is 1. So 1 times x will give you x raised to the power of 2. S raised to the power of 2. So what is now going to be our x? Our x is now equal to the square root of KSP. Our S, because we are going to be doing square root of both sides, our S is going to be equal to the square root of KSP. And we already got our KSP is 1.78 times 10 raised to the power of minus 10. So our square root now is square root of 1.78 times 10 raised to the power of minus 10. So if you press that in your calculator, ensure you put the 1.78 times 10 raised to the power of minus 10 in a bracket. You are going to have, if you press that in the calculator, you are going to have 1.334 times 10 raised to the power of minus 5. So the solubility of silver chloride is going to be given as 1.334 times 10 raised to the power of minus 5 mole per dm cube. Alright, so the next question we're going to be having here is the solubility of barium chloride. Solubility of barium chloride at 25 degrees Celsius is 3 times 10 to the power of minus 5 mole per dm cube. Find the solubility product of this source. So barium chloride will dissociate into Ba plus 2Cl minus. So what it means is that you have 2 chloride there and then you have 1 barium there. So our KSP is equal to S. Our KSP is equal to S raised to the power of, what's going to be our S? Since it's 1 barium we are going to have 1, and our Y, since it's 2 chloride we are going to have 2. Then it's now with dot 1 raised to the power of 1 dot 2 raised to the power of 2. Why 2? Because we have 2 chloride. Why 1? Because we have 1 barium. So we're going to have this equal to 2 times 2 will give us 2 times 2. This is 2 raised to the power of 2, so that is 2 times 2. 2 times 2 is 4. 4 times 1 is 1. 4 times x will give us 4. 4x. 1 plus 2 is 3. So that is 4x raised to the power of 3. Now we were given the solubility. We are supposed to look for the KSP, which is the solubility product. So can we be able to do that? Our KSP is equal to 4 brackets 3 times 10 raised to the power of minus 5 raised to the power of 3. So let us do that very quickly. 3 times 10 raised to the power of minus 5 raised to the power of 3 times 4. Our KSP is equal to 1.08 times 10 raised to the power of minus 13. 1.08 times 10 raised to the power of minus 13. And then the next thing we have to focus on is on the units. Now we are aware that what we have here is mole per dm cube. Mole per dm cube. So what it means is that when S was cubed, the mole will automatically become mole cube per dm raised to the power of 9. Dm raised to the power of 9. We have dm raised to the power of 9. So because we have this also being cubed. So we have mole cube dm raised to the power of 9. So we have 3 times 3 as 9. So this is the unit for this. If this was going to be 4, what you're going to have is mole raised to the power of 4, dm raised to the power of 12. If this is going to be 5, you're going to have mole raised to the power of 5, dm raised to the power of 15. What you just simply do is you do the cube of this and then multiply this by whatever superscript you have there. So that's the solubility product of barium chloride. So we're going to look at one more example of solubility product. We're going to look at common ion effect. We'll solve some exercises and this particular tutorial video will be over. Alright, so we're going to be calculating the last example on solubility products, and then we'll do common ion effect, and we'll look at some of the challenging exercise questions, and then that will be the end of the tutorial video. Remember, just in case you get confused at any point, you can ask your questions in the comment section, and then the academic team will reach out to you from NSCPS, and you can always reach out to any executive of the NSCPS Executive Council for you to gain guidance in any area where you are confused. Alright, so let us look at the question. It says calculate the solubility product for barium chloride if the concentrations of barium is 1.25 times 10 to the power of 5 mole per dm cube and Cl minus is 3.20 times 10 to the power of minus 4. Remember I told you that when you have something like Mp and then you have N cube, what you're going to have there is going to be concentration of N plus raised to the power of P, then concentration of N minus raised to the power of Q. So that's what we're going to be having here. So this is barium chloride dissociating into Ba plus 2Cl minus. So what we're going to be having there for the KSP is going to be KSP is equal to the concentration of barium plus raised to the power of 1, since it has a subscript of 1, and then Cl minus raised to the power of 2, since it has a subscript of 2. What's the concentration of barium chloride? Barium, we are told that the concentration of barium is 1.25 times 10 raised to the power of minus 5, and then raised to the power of 1, multiplied by the concentration of the chloride is 3.20 times 10 raised to the power of minus 4 raised to the power of 2. So that's going to give us what now? Our KSP. Our KSP is equal to, so I have 1.25 times 10 raised to the power of minus 5 times, in brackets, 3.2 times 10 raised to the power of minus 4 raised to the power of 2. And then what we're going to be having there is equal to 1.28 times 10 raised to the power of minus 12. What we have there is 1.28 times 10 raised to the power of minus 12. 1.28 times 10 raised to the power of minus 12. Then the next thing we're going to be considering is going to be the units. The unit for the concentration is mole per dm cube. So for the barium, you still have mole over dm cube. And then for the chloride, you have mole over dm cube, and everything is raised to the power of 2. Indices. This will now be mole over dm cube times mole raised to the power of 2 divided by dm cube raised to the power of 3 times 2. Mole times mole raised to the power of 2 is going to give us mole raised to the power of 3, and then dm 3 times 2 is that's 3 times 2, that's 6. 6 times 3 is going to give us 18. 6 times 3 is going to give us 18. Okay, I think I'm quite confused there. Oh my god. Okay, so I think there's somewhat of a challenge we're going to be having here. We're going to be having somewhat of a challenge in this particular place, but this is supposed to end in a dm raised to the power of 9. So, but then I can figure this out later. But in the meantime, just know that what we have here is mole raised to the power of 3 per dm raised to the power of 9. So that is that about that particular calculation. That is that about that particular calculation. So, that's that about that particular calculation. So this is actually, what this actually looks like is more like you're doing x times x raised to the power of 2. If you're doing x times x raised to the power of 2, that's actually x raised to the power of 3. Are you following? So when you do dm3 times dm3 raised to the power of 2, what you're simply doing is more like dm3 raised to the power of 1 plus 2. That's going to be dm3 raised to the power of 3, and that will be dm raised to the power of 9. So this is simple indices. I'm just trying to break it down to ensure that you understand it very clearly. So you can look at this again before I wipe it off. So this is what you're going to end that as your units for the calculation. So depending on the kind of exams you have, it will determine which of these are very important for you to take note of. So the next one is common ion effect. You have sparingly soluble salts. Sparingly soluble salts or partially soluble salts, in the presence of common ions, their solubility is going to be decreased. When you have them just in water, they are sparingly soluble, they are partially soluble. In the presence of common ions, the solubility is going to decrease. That's what we call common ion effect. And for you to calculate the solubility in the presence of a common ion, you simply do KSP divided by the concentration of the common ion raised to the power of coefficient of common ion. Now pay attention to this. Pay attention to this. Now, the concentration of the common ion used, is from the solution. The concentration of the common ion used is from the solution. Meanwhile, the coefficient the coefficient of common ion that is used is from the salts being dissolved. This can play a very, very serious trick on you, and once you interchange it, you will get an option that will be in the option but will not be the correct option. So the concentration of the common ion used is the concentration from the common ion in the solution, while the coefficient of the common ion used is the coefficient from the salt that is being dissolved in that particular solution. I hope you got that very clearly. So let us look at some examples for us to highlight what we are talking about here. It said that given that the KSP of radium tetrasulfate, tetraoxosulfate 6, RaSO4 is 4.0 times 10 to the power of minus 11, calculate its solubility in 0.100 mole per dm cube of sodium tetraoxosulfate 6. Now, do you see that this is tetraoxosulfate 6 and this is tetraoxosulfate 6? So there's a common ion already. Radium tetraoxosulfate 6 is already sparingly or partially soluble in water. In the presence of sodium tetraoxosulfate 6, in that same substance supposed to be soluble in, it will decrease the solubility. So we want to now calculate the solubility in the presence of sodium tetraoxosulfate 6 is 0.100 mole per dm cube. So the first thing for you to do is to run the dissociation equation. You run the dissociation equation, so it dissociates into Ra plus Ra2 plus SO4 2 minus, and then for sodium sulfate dissociates into Na plus 2Na plus SO4 2 minus. So the next thing for us to now write is to write the formula for solubility. Now our solubility is equal to KSP. What is the KSP of the radium tetraoxosulfate 6? The KSP of radium tetraoxosulfate 6, which is the KSP of the source that you are looking at, is 4.0 times 10 to the power of 11, 4.0 times 10 to the power of minus 11. Then the next thing you have to now do is to find the concentration of the common ion from the solution, and the solution we're talking about here is sodium sulfate solution, and the common ion here is sulfate, and this reaction is a 1:2:1 reaction. So for every 1 mole of sodium tetraoxosulfate 6, you have 2 moles of sodium ion and 1 mole of sulfate ion. So what it simply means is that for 0.1 mole of sodium tetraoxosulfate 6, you get 0.2 mole of sodium and you get 0.1 mole of sulfate. So what's of interest to us here is this and this. So since it is 1:1, it means that the concentration of the sodium tetraoxosulfate 6 will be the same thing as the concentration of the common ion here. So we simply have 0.1. And then the coefficient, that's why the coefficient we are going to use is the coefficient of common ion from the salt that is being dissolved. According to this question, the salt that is being dissolved is radium tetraoxosulfate 6. So we are going to be working with radium tetraoxosulfate 6, and the coefficient here is 1. So the coefficient we are going to have here is 1. So for you to work on this will now be 4.0 times 10 raised to the power of minus 11 divided by 0.1, that is raised to the power of 1. So this is going to be 4.0 times 10 raised to the power of minus 10. So mole per dm cube. So this is the solubility of the radium tetraoxosulfate 6. So this is the solubility in water, but this is the solubility in sodium tetraoxosulfate 6, in 0.1 mole of sodium tetraoxosulfate 6. So this is actually higher than this particular value. This is actually higher than that particular value. So that is that about that. So let us look at number 2. So calculate the solubility of silver chloride in a solution of 0.02 mole per dm cube of KCl if the solubility in water is 0.01 mole per dm cube at 25 degrees Celsius, given that its solubility product is 1.78 times 10 raised to the power of minus 10. Given that its solubility product is 1.78 times 10 raised to the power of minus 10. Alright, so what we have here is for silver chloride. So silver chloride will dissociate to give Ag plus Cl minus, and then KCl will dissociate to give K plus Cl minus. So what it simply said is calculate the solubility of silver chloride in a solution of 0.02 mole per dm cube KCl if the solubility in water is 0.01 mole per dm cube at 25 degrees Celsius, given that its solubility product is 1.78 times 10 to the power of minus 10. Now we have a problem with this particular question. When you look at your material, the material solved using 0.01 mole per dm cube to get the solubility product. But this particular question already gave us the solubility product. So one of these two things will be wrong. It's either this one is wrong or this particular one is wrong. But then in a same situation, in a normal situation, if you have the solubility in water and you have the solubility product provided to you, which of them is more easier to use? Your formula says solubility is equal to KSP over concentration of common ion raised to the power of concentration of common ion. So we're going to be working straight with the solubility product and ignore the solubility in water that was provided for us, because that is the simplest way for us to solve it. So our solubility is equal to KSP. What is KSP? KSP, according to the question, is 1.78 times 10 to the power of minus 10, and then the concentration of the common ion. I said the concentration is the one from the solution, and the solution is 0.02 mole per dm cube of KCl. Since it is 1:1, the common ion here is Cl, this is 1:1, so it means that 0.02 mole of KCl will give us 0.02 mole of Cl, since it's a 1:1 reaction, so we have 0.02, and then I said the concentration, the coefficient you are going to use is from the salt that is being dissolved, and the salt that is being dissolved here happens to be AgCl, and the coefficient is 1, so it's going to be raised to the power of 1. So what we're going to have here is 1.78 times 10 to the power of minus 10 divided by 0.02, and that's going to give us 8.9 times 10 to the power of minus 9 mole per dm cube. So this is going to be the end of the main material in this tutorial. So we look at a few calculations in the exercises. Meanwhile, you can check the link in the description below, and you'll see the link to the solving of all the exercises that are available in the material provided for this particular tutorial. We'll look at a few of them, and that will bring us to the close of the lecture. So let's make progress. Alright, so we'll just do one exercise in the study question. Looking at the link in the description below, you'll find the document that contains the solution to all the study questions. But why we need to solve this is because of the application of that concentration and coefficient, so you can see what will happen if you eventually cause an alternation to it. And I'll just give you some final tips to prepare you for your chem, and then that will be the end of the tutorial. The question said determine the solubility of AgCl in 0.100 mole per dm cube BaCl2. So you can see Cl here and Cl. What it comes to your mind is common ion effect. So the first thing for you to write is write the dissociation of AgCl. You write the dissociation of AgCl, and that is going to be AgCl dissociating into Ag plus Cl minus, and then the next one you have is for barium. You have barium chloride dissociating into Ba2 plus Cl minus, 2 moles of Cl minus. So the next thing for you to write is to write the formula. We know that solubility is equal to Ksp divided by concentration of common ion raised to the power of coefficient of the common ion. So what is the Ksp of the AgCl? It is 1.0 times 10 raised to the power of minus 10. And then the concentration, I told you before that the concentration we are working with is the concentration of the solution in which you want to dissolve the salt. This question says that the solubility of AgCl in 0.100 mole per dm cube of BaCl2. So where you are dissolving the salt into is BaCl2. So you need to get the concentration of the common ion in BaCl2. Now BaCl2 is a 1:1:2 dissociation formula. So what it simply means that 1 mole of barium chloride will give 2 mole of chloride ion. 1 mole of barium chloride will give 2 mole of chloride ion. So 0.1 mole of barium chloride will give you 0.2 mole of chloride ion. 1 mole will give you 2 mole, 0.1 mole will give you 0.2 mole. So what it means that the concentration of the common ion you are going to have there is 0.2 2. The moment you miss it and you just put 0.1, your answer is going to get wrong. That was why I emphasized it when we are doing the normal examples. The next thing is coefficient. I said the coefficient I'm going to use is the coefficient of the salt you are trying to dissolve. You will realize that the coefficient of chloride in AgCl is 1, but the coefficient in barium chloride is 2. At this point, a student can get confused and ask, should I use 1 or should I use 2? I've made it very clear. The coefficient you are going to use is the coefficient of the salt you are trying to dissolve. And in this case, the salt you are trying to dissolve is AgCl. So the coefficient of Cl there is 1, because this is a 1:1:1 reaction. So there's no, it's just, this is a 1 in front of the Cl. So that's 1.0 times 10 raised to the power of minus 10 divided by 0.2 raised to the power of 1. So that's 1 times 10 raised to the power of minus 10 divided by 0.2, and our solubility is going to be 5.0 times 10 raised to the power of minus 10. So this is the solubility. This will be mole per dm cube. So this is solubility of AgCl in 0.1 mole per dm cube of barium chloride. So this is going to be the end of the tutorial on chemical and ionic equilibra. Now let me just give you a few tips. For this particular course, you could write it as a theory, you could write it as an objective. If you're going to be writing it as an objective, take note of the fact that your questions will not be complex, because Chem has a culture of making sure that their time is very limited, and at the same time give you questions that you should be able to attempt within such a limited time. So you will not have complex questions like the ICE table kind of questions and the likes in an objective examination. But if it's a theory examination, you most likely find those kind of questions or even much more complex questions featuring depending on the taste of the lecturer at that particular point in time. So do well to sit down, try out the study exercises, use the link in the description to locate the particular solution to the study questions, try out as many calculations as possible. If you have past questions, you can look them up, prepare for the other areas of chem, like the order of reaction, like the area on thermodynamics, and the area on drug molecules, properties of drug molecules. Thank you so much, and don't forget, this is coming from the National Fellowship of Christian Pharmacy Students, NFCPS, UNN chapter. Do have a nice day. I remember my humble self, Ede David Chibuzo.